Okay, thank you, Masashi. And as usual, it's a huge pleasure to come back to Japan and Tokyo. It's again, as usual, it has not disappointed. And so today, what I really want to sort of focus on is to try and give you an overview of some of the challenges in robotics and AI that we are addressing, and particularly pick up on two very small pieces of the technical aspects. So I don't need to impress upon you guys that robotics is becoming ubiquitous in different parts of our lives, all the way from things like applications in manufacturing to outer space, to things like autonomous driving cars and smart cities, also applications for the care of the aged and assisted living. So there's a huge impetus on making robots a lot more robust and versatile compared to the robots that were used in factories, for example. So in terms of paradigms, so we used to have paradigms of teleoperation, and this is what I call sort of automation, where you program a robot to do something, or you get them to repeat something again and again, to research in autonomy, where you're trying to get robots to make decisions on their own. But really, the challenge, in my opinion, is somewhere in between, where there is a seamless transition between autonomous behaviors and teleoperated or human-in-the-loop behaviors, depending upon the circumstances that we have to tackle, depending on the task, depending on the circumstances. So we need to think about some additional challenges that this sort of three-way or three-person or three-agent systems bring into the story. Basically, things like unconstrained environments, highly noisy environments, and pretty hard to model dynamics. So these things bring additional challenges that traditional model-based methods of robotics is not being able to solve. So there are also other socioeconomic reasons. Again, I'm not going to spend a huge amount of time on that, but I think it is by now well understood that we need robots to maintain our infrastructure. We need robots to do inspection of assets, work in dangerous places, and do it at scale, because we've got an aging population and maintenance of infrastructure is really, really hard. So what I want to do today is to start by giving you a motivating example of a particular robotic application, and then try to break down the science that needs to be solved to address that. So let's take an example of robots in an offshore oil and gas platform. So this is about 5, 6, 7 years ago. We did some sort of mock-up tests of robots that needs to navigate in environments that are extremely complex. So non-flat surfaces, it has to walk on stairs, walk in extremely slippery environments, in this case on an oil and gas platform. So this was the state of the art sort of 5, 6, 7 years ago. So the building the hardware is one thing, but trying to put smarts into it is an extremely challenging element, part of it. So we broke that challenge down into various bits and pieces. And what I'm going to show you next here is a little slide of a scaled mock-up in our lab of the environment that you saw before. And in that, the robot has to do various tasks. For example, it has to use its 4 legs to go and turn a valve. It has to then go to a panel nearby and open and operate a lever. Then it has to climb up this ramp and open a gate, and then pull a bucket up for which the weight of the bucket is unknown. So if you want to sort of realize this sequence of operations, what I'm going to show you is the final output of what we have managed to do. And this is, again, not very many labs in the world or even companies are able to do this at this level of robustness. And you can see here the 4-legged robot. What you need to sort of, I'm going to pause it here. What you need to see in the legend here is it sort of shifts between a teleoperation mode and an autonomous mode. So under the teleoperation mode, especially things like walking, you have a person joysticking it towards a particular direction but not controlling the individual legs, but just giving the direction. And then once it reaches its post, the robot has to make a decision on its own in terms of the pose of the robot, so that it is robust to so that it is robust to disturbances, so that it is robust to external perturbations, so that it is able to do the task. So for example, now it has just gone from an autonomous mode to a teleoperation mode. Then you bring it near the task and then switch back to autonomous mode, where the robot adjusts its whole body pose and posture to make sure it is robust to external disturbances, and then sort of continues on, switches back to the autonomous mode. So here's the autonomous mode. Now we switch to the teleoperation mode, where you joystick it to walk across the ramp, and then it sort of goes and so the important part is that the pose of the robot, the whole body pose, is not predetermined. Depending upon the operation it has to do, you will see that the legs, they go into different modes, which is optimized based on certain things that I'm going to talk about later. So there's the optimal control elements, which optimizes robustness to external disturbances, optimizes the pose related to stability and the uncertainty. For example, the next task that the robot has to do is to pull a bucket of unknown weight. And in trying to do that, you will have to it has to be robust against a class of functions it is effectively an external perturbation that is unknown. And again, here now it localizes the place and it switches back to an autonomous mode, where the pose of the robot is decided from first principles to then so it will start pulling, and then based on the sensory motor feedback it gets, it adjusts its pose in response to the weight of the system. So again, none of these is done by hand. It is a fully autonomous operation that happens on the fly. Okay, so if I now break this output or the result of many bits and pieces that I've shown into pieces that is required to solve this. So for those of you who are not familiar with robotics, so this is the basic sensory motor control diagram, which goes from a planner to a controller, biomechanical plant to an estimator. And now if I look inside this yellow box, or what we call the controller, if I formalize what is inside that yellow box or the controller, you can just describe it very briefly in sort of one slide, which is saying that you have some start and end states, you've got a time horizon, and you have some system dynamics, that you have a kind of discrete part and a stochastic element, stochastic part. You have a cost function, which is a combination of some sort of final costs, and this could be a reaching task to reach to a particular location, and you've got some running costs like energy, efficiency, robustness in terms of trajectory tracking. And then in theory, you can take your favorite optimal control solver. The most simplest ones are ILQG, things like iterative linear quadratic regulators, or other more sophisticated planners, nonlinear planners like SNOPT and IPOPT to solve this. So what comes out of something like an optimal control framework is literally you have some cost functions, dynamic models, and what comes out is a series of output commands and some gains. So these gains are directly proportional to the uncertainty of the model. So if you want to try and solve this, there are some fundamental questions you need to answer. Okay, so I've listed 4 kind of key questions that needs to be choices that need to be made when you're doing planning with optimal control. So dynamic transition models, representation, choice of cost functions, and how do you exploit natural dynamics by exploiting things like variable impedance. So I won't have the time to go through all 4 bits of the pieces today. So I'm going to pick up on 2 things, the number 2 and the number 4 in slightly more detail to talk about today. Okay. But however, I do want to point out that pretty much half my life I've dedicated to the number one question of learning dynamics on the fly using machine learning techniques. So there's a lot of work that we've done in our group. We continue to do, looking at learning and acquiring dynamic models on the fly incrementally. And I have one slide just to tell you where all of that fits in, without going into the details of the learning aspect, right? So this is the traditional sort of learning control diagram or flow chart, which says cost function, analytical dynamics, optimal control. You have your noise and control law. But what we've done is we've replaced that analytical dynamics box with a learning loop where we get dynamics data on the fly when the robot operates. We use an internal model learning framework to then sort of worry or learn about changes in the dynamics, but not just learn the change dynamics, but we also want to learn the underlying uncertainty. So what we're doing is we're doing optimal feedback control with learn dynamics, where we've got the underlying uncertainty built into the effectively the solution that comes out will take into account this underlying uncertainty when we build this on the fly. But what I want to talk more in detail today is something about representations. Okay, so what are the kind of representations that are suitable for doing very complex tasks in robotics? So I want to give you an overview slide before going into some of the details. So if you want a robot to reach into a box, then you can do it in many number of different ways. You can use Euclidean spaces to kind of reach into it. But the problem is there are some issues with representation scalability of these methods. So we've been for various different kinds of applications. So reaching, manipulating objects, grasping, manipulating flexible objects like ropes. We've been looking at different kinds of representations based on topological constructs to deal with that. Okay, so let me start by showing you a quick video. Oops. Yeah, of exactly what I mean by topological constructs. So, for example, you could have a robot arm reach into this box. I could specify this with X, Y, and Z. But if I use topological constructs to represent both the goal and the environment, then when the box moves, the concept of what is inside and outside the box moves with the space. So because of that, I can then, if my goal is not in Euclidean space, but in topological space, then I get replanning for free, because all I'm saying is I'm going to do gradients in topological space, which is trying to maintain the status quo, which is I'm going to go into a bit more detail later, but effectively, if we live in that space, you're able to do that much more effectively. So intuitively, the one slide sort of intuition behind it is in task space or joint space, some of these spaces look horribly complicated if you try to navigate it, do gradients on that for planning or for control. But if you use the right representation in terms of either relational representations or say things like right spaces where the coils or number of times a continuum robot is wound around it, then you can specify goals which become linear in that space. So you can use much more dumb local planning algorithms if the representation is right. So what are the kind of things that we've explored? We've explored in this slide, it has the different kinds of things we've explored. So the one on the right is what we call interaction mesh. I'll go into a bit more detail later. The one in the middle is electrostatics, based on electrostatics of charged particles. And the one on the left is based on read graphs. So, and all of them have served different purposes. The read graph one looks are topologies that are very useful for motion planning in space. The one in the middle is useful for grasping with fingers. And one on the right is useful for sort of a human-robot interaction. And I'll give you examples of each of these things, okay? So the right spaces. So what is the concept of right? So a right is a topological concept which is looking at mapping the relationship of curved objects around another object. So in simple terms, if you have a rope that is coiling around this central stick, a right of 1 would mean it's coiled around once, a right of 2 would mean it's coiled around twice. Okay, so if I want, for example, a snake robot that climbs up a tree or does something else, so instead of providing Euclidean coordinates in terms of every joint in X, Y, and Z, and then specifying a gradient or a motion plan in that space, I could literally say, I want it to go from right 0 to right 2. Okay. So first of all, the advantage is that the space becomes a lot more sort of linear. Secondly, it automatically captures invariance, because sometimes you don't care about how tightly I wrap around the stick. I only care about, is it wrapped at all? So those kind of natural invariances in motor control can be captured using some of these topological constructs. Similarly, for grasping, we can use a concept based on potential field and electrostatics. So why do we care about this? So the traditional Euclidean distance-based sort of things. So if I've got 5 fingers, if I want to create a motion plan to grasp an object, typically when in the process of specifying a start goal and an end goal and a trajectory of each of these fingers, you will have lots of local minima in the space of these trajectories. But if I, for example, use some representations based on harmonic fields, so they are nothing but, if you think about it, if you sort of take a charged particle and trace the electrical fields that emanate from the charged particle, the good thing is that they are by design, they are non-intersecting, and because of that, you can do gradients in that space which will not have the same problems as lots of local minima in certain spaces. Of course, it's a different beast if you have got 2 intersecting electrostatic fields. Okay, that's a different setup. But effectively, you can think of it like parameterization based on some electric charge, and then you would take those electric charges, you would project it onto the space of your action space. So you would do a projection onto this action space and specify, and you will get the motion plan for free. Why? Because there is a relationship between electrostatic forces and projection and flux. Flux is the change. Okay, so what I can do is I can take an electrostatic charge and I can say that if I want an arm to grasp that bottle, I can say that I want the flux, the change of flux, to move from the position on the left to the position on the right in the space of electrostatic coordinates. So compared to Euclidean ways of representing this, it becomes a lot more nicer. The space of actions become a lot more nicer. Another representation which is very, very useful is what we call interaction mesh, where the main focus is not where I am with respect to the world or where the robot is with respect to the world. The main focus of this representation is relational representations. Means, where is my hand with respect to this object, or where is my leg with respect to a particular object? Okay, and so if I do that, then you can do very, very clever things like, especially when we have got human-robot interactions or human-human interactions, you can represent these motions using these metrics and meshes. And all you can talk about in terms of when you do planning is the deformation between these meshes. So if you talk about the deformation between these meshes, and if I say, I want to say, maintain this deformation, or I want you to change the deformation from this to the other, there are methods that can do this very effectively. So for example, I'll show you a quick video of exactly doing that in real time. So we have a human with some markers tracking that's the dot, the humans, but you can see, let me just pause here for a bit. So what you'll see is that not every point on the human or the environment is marked as a point that's relevant for the mesh. So you can selectively pick up certain elements of the mesh that is relevant for the task at hand. And then you specify a goal which says that I want to maintain this relational status between the arm and the human. And the motion planning comes out as a byproduct of that. Yeah. So basically the obstacle avoidance and the motion plan in terms of what the arm, individual joints of the arm should do, comes out as a byproduct of the human moving into that space, because all it's doing is maintaining the mesh structure, the interaction mesh structure in the relational space. So I'm going to jump through this in terms of the interest of time, but the same concept. So topology is very nice because you've got a huge set of operators that you can use to you can exploit. So just like, if you can frame a problem into a Bayesian inference mechanism, then you can exploit the whole sort of tool set of Monte Carlo estimations and approximations, etc. Similarly, topology has got a huge tool set which you can get for free. So for one such concept is homotopy. So homotopy is when you can transform one sort of pose or trajectory or sort of navigation path to another without changing topology. Okay, so and you can find equivalences in or what we call homotopy classes that can then be exploited for motion planning. So why is this? So for example, the figure that you see on the left is a robot trying to do a saran wrap over a bottle, right? So it has got many relational elements in terms of how does the two, the wrapping piece, how does it connect to the two arms, and how is it in relation to the bottle. So even if it starts really far away and the bottle is here, as long as it does not change topology, in other words, it does not change the wrap doesn't go underneath the bottle, it belongs to the same class of functions or the same class of trajectories. So using these homotopy classes, you can first of all ensure that the local minima or motion planning methods which do not have guarantees of global minima still work, because you can ensure that you live in the right homotopy class of the function that so you only care about that. So similarly, if you want to look at trajectories of robots in space, you can capture that in homotopy classes, so that whether you're navigating or whether you're doing stuff, you can fundamentally make a difference between is it in the right homotopy class or not. So, but fundamentally, the advantage, why is it very useful and practical, is because you can use locally convergent algorithms or local optimizers for doing things very fast. Similarly, the other concept that we've been exploiting, and some of the details are in some of the papers that we published, is this notion of persistent homology. So, in particular, if you think about navigating in a complex space, typically a robot has got, say, 2 or 4 wheels. Okay, so there is a fundamental problem in trying to do navigation. You have to figure out, if you've got 4 wheels, whether this wheel has enough, can you actually navigate through a particular space, and if there is a hole or some sort of obstacle, is it wide enough to either go over the hole or can it avoid the hole? So those are the kind of problems that we have to tackle in motion planning, because most robots are not blocks of squares, very homogeneous stuff. So because of that, we have to look at these concepts of persistent homology so this is effectively a filtration in the space of topology, where you look at the problem at different scales. So you can take a robot and look at it and say that this robot consists of 1 meter blocks, okay? Or then I can say, no, actually this robot is built of 50 centimeter blocks, or this robot is built out of 100 centimeter blocks. So all of these will give you different filtrations or homologies in the space, and based on the right level of say hierarchical distribution, you can find out whether a motion plan is valid or not in the space of the motion plan. So effectively, this is a tool to be able to work with non-homogeneous discrete features in the robot space while doing planning in very, very local ways. And again, we've used this kind of concepts. So this is a paper that we presented 2 years ago on using persistent homology for trajectory optimization of a humanoid robot. So effectively multi-limb, multi-degree of freedom robot. And very simple question of reaching over something is very complex for a multi-limb robot because of exactly this problem that I've been talking about. So that was mostly about use of topology in representation of the environment and the world, and we've been using this to then actually do the problems that we really care about. So things like a robot perceiving the world, going from raw perception to on the fly building topological constructs of what are steppable surfaces and non-steppable surfaces. From that, using local planning methods. One of the local planning methods is called SLIM. So using that to then understand what is the affordances in terms of the stepping elements that the robot can do, and then on the fly create motion plans and then do control on top. So so what I talked about in terms of the representation is just one step in enabling these motion plans to happen on the fly fast enough so that you can update this. Otherwise, there is no hope in hell using classical Euclidean methods to do this using what we call model predictive control. So if you look here, you can see the perception is very local. It does not have a long horizon view. It's building the perception on the fly while the robot's climbing. So these are the kind of challenges that we kind of bring together concepts from topology and motion control to solve some sort of real world problems, especially in unstructured environments that which we don't know about. So this concept, we've been using it for many other robots, like full humanoid robots walking on uneven terrain. So this is our NASA Valkyrie robot walking on extremely uneven terrain. Again, real-time perception, motion planning on the fly, and then whole body control. So I'm going to talk about one more thing, not in as much detail as this one in the interest of time. So the other aspect I'm very interested in is exploitation of natural dynamics, effectively doing variable impedance. So change of dynamics. How do we use impedance changes? And we want to do this impedance change. So let me first show you what I mean by impedance change. Okay, so this is a simple toy thing that we set up in our lab to show people the concept of impedance. So if you move your hand, you can move your hand using just one muscle at a time, or I can co-contract my muscle and move the robot arm, or my arm. What's the difference between co-contracted movement and a movement which uses only one muscle? the difference is that if I get an external perturbation, then when I co-contract, it is naturally robust against external perturbations at the expense of energy. Okay, so this is an example of adjusting impedance or variable impedance to be robust, naturally robust against external perturbations without doing active control. So what I want to get across is that by adjusting stiffness, you can do very interesting things for things like brachiation, throwing, walking, jumping, by optimizing variable stiffness on the fly. So again, I will just quickly skim through this, and please come and find me if you've got detailed questions. But I'll just show you some, the concepts that we've been using is exactly the thing that I talked about with respect to optimal control. So you've got a model dynamics, you've got a cost function, you've got an optimal control solver, but now the elements that you're trying to solve for are not just redundancy in kinematics, redundancy in dynamics, but you're also solving the redundancy in impedance as first principles of cost function. And you're given a particular thing. I want to throw fast, I want to be robust against perturbation, I want to be X, Y, and Z. So your cost function changes the stiffness parameters that comes out. And how do we solve that? We have a nice interface to machine learning here, where this is already sort of 10-year-old work now. So we had a paper at RSS on the equivalence between optimal control and reinforcement learning through approximate inference. And this work gives us the bridge between solving optimal control using traditional model-based or sampling-based methods to using Bayesian inference techniques to then solve that on the fly. So we can convert this problem into a graphical model-based inference techniques. This is work that we did when Marc Touzon was a postdoc in our group. And then we now use that extensively to do multi-scale planning by inference. And where that fits in is that you can use these hidden variables as the alternate representations that I've been talking about. So all the rights, the interaction mesh, all of those things are intermediate representations on which you can do the planning, but you can maintain consistency across the different modalities of sensory space. So whether it is in joint space or task space or this intermediate topological space, you can maintain consistency across these spaces by just adding additional layers, and then use the full inference mechanisms to solve the actual, to get out the policies effectively. So what comes out of solving such things? You can actually selectively change the stiffness of the robot in different directions depending upon the task that you do. But more interestingly, I'm going to skip this. More interestingly, you can actually compute the stiffness adjustments while a robot is walking and it sees an external, external disturbance, a variable impedance modulation based on the principles that we just talked about, make the robot it makes an actual difference in terms of the robot not seizing up and adjusting the stiffness and its motion plans. So it's a bit hard to see, but yeah, you're already seeing here that's sort of seized up because it's seen unexpected perturbations. But on that one there, the stiffness modulation is already helping me adjust that on the fly and then sort of navigate on terrain. Okay, I'm really running short of time, so I'm going to skip quite a few slides, and actually I'm not going to get to the exoskeleton stuff. Let me just, oh yeah, so a few things I do want to sort of say. So if you go down to, has anybody been to the robot cafe? Yeah, no, you guys haven't been to the robot cafe. Okay, I actually don't know exactly where it is, but if you Google and search up robot cafe, okay. So some of the work that we've done with this stuff in collaboration with Kawada is now deployed as a robot on the robot cafe in Tokyo. And the whole point of this is we can do teleoper. So there are some people operating these robots from different parts of Japan, from Osaka, from wherever, and these are people who are either disabled or have some sort of mobility issues, are paraplegics, who are effectively teleoperating this device. So for example, the voice and the camera feed is live. So the people can actually see, and the voice you hear are of the people who are operating this. But the robot is making autonomous decisions on its own in terms of picking stuff up, avoiding obstacles, grasping objects, actually opening the thing, pouring hot water into it, making a tea, and actually it serves the tea to the customer. So it's a little bit of a gimmick, but it actually shows how the notion of avatar and presence can be used for example, in this case, getting people who are out of the workforce back into the workforce, right? So I won't have the time to kind of play this through, but really exciting sort of developments, real world applications. I'm also going to skip this. Please come and ask me for this, because this is something. This is the work that I'm really passionate about now in terms of using robots for exoskeletons. So adaptive assistive robotic systems for human-robot interaction. Really using, we've been doing some work with MND patients and multiple sclerosis patients on gait analysis. So all the insight that we've got from controlling humanoid robots, we can now go back and look into pathologies in human neurodegenerative diseases and looking at how we can kind of look at the progression of this. So unfortunately, I don't have the time to go into this, but let me just quickly show you the sort of framework in which we've been using this. We've been using this in the framework of using exoskeletons and FES, so functional electrical stimulation. So this is a 3-agent, not dyadic, but triadic collaboration. So you've got the residual forces of the muscles of the humans. You've got the exoskeleton that is helping the human work, but also functional electric stimulation on the residual muscles. So the whole idea is as neat assistance to ensure the rehabilitation can progress on the fly. Okay, so I think I'm almost out of time. So I'm going to play one last video, and I'm going to skip all the other things. You can come and ask me for these things. This is nice Center for Robotics where we're looking at very much like RIKEN, taking some of the research from the labs to the market to innovation, and then the Turing stuff is asking some moral and ethical questions behind deployment of these things. And so we've got some living labs and digital labs. So a 2-minute video that shows all the people behind the scenes who've been doing all the hard work, the postdocs, the PhD students, but also the range of things that I didn't get a chance to speak about. Statistical machine learning and motor control group at the University of Edinburgh. Here we do exciting world-leading research on robotics, machine learning, and data-driven techniques using artificial intelligence to make robots a lot more versatile and adaptive to the real-world situations. We do work across domains, so applying the core problems in robotics and machine learning to domains in oil and gas, transport, healthcare, as well as things like the challenges of exploration in outer space.
We want our robots to be autonomously deployed in industrial plants, for instance, to perform inspection tasks, to accomplish tasks that humans can't do or that are dangerous for them.
Our main business is to educate the next generation of outstanding postgraduate students and conduct cutting-edge research.
My research is focused on designing exoskeleton controllers that can assist people completing tasks such as walking. And to achieve this, what we do is we build quite complex neuromuscular models of human subjects and combine this with a very detailed set of motion data that we can collect in our gait lab.
We hope that with this setup and combining robotic assistance with electrical stimulation, physical therapists can have a tool to personalize the intervention and improve the outcomes of physical therapy.
My research is about robot localization in changing environments.
when the robot's view is nearly occluded by large moving objects.
We want the robot to learn which objects are of interest without requiring a human to provide information about the shape or the visual appearance of these objects.
In order to enable robots to move while in contact, for example, when wiping a table or pushing a heavy object, my research focuses on how to plan or how to learn those types of physical contact interactions.
We are developing mathematical models to enable a robot to capture heavy and moving objects with 2 arms. At the same time, we are handling impact.
My research involves both humans and robots, where first we enable the robots to predict humans' intentions and actions, and we also generate safe robot actions in order to help the humans reach their goal.
In construction, robots are often operated by humans in dangerous environments, needing expensive training. To reduce the operator burden, I'm working on shared autonomy, which combines human input and autonomous methods so the human can best utilize their expertise.
I'm really interested in human-robot collaboration, so how we can enable robots to perform a common task effectively with a human, such as pouring a wine into a human's glass. Humans are really difficult to predict, and so I'm interested in how we can better make those predictions.
I'm working on the development of robots that can be easily taught to manipulate objects and potentially collaborate with people or assist people in need just by giving a demonstration of the task.
I'm working on leg robot to make them traverse challenging terrains. The idea we propose is to start with a capable controller that already works on the robot and try to extend and add capabilities to make the robot cross challenging terrains.
I'm working as a software engineer in a field robotics lab, and also I'm doing some research about quadruped robots. I'm working on how those robots with 4 legs should plan their footsteps considering the torque limits on their legs.
When robots have to perform manipulation and walk simultaneously, they face a lot of uncertainty. One way we can increase the robustness of the system is by taking into account the capabilities of the robot, so its motors and also the contact stability.
There are many conditions that we cannot predict. For instance, when we are navigating an offshore platform, we might encounter a floor that is wet. A way of dealing with this kind of uncertainties is by replanning quickly new modules.
I'm working on building better robots for specific tasks. So a robot that walks might need to be built a little differently than one that jumps. And so I'm working to create algorithms that modify the designs based on the tasks. And I'm looking at making those more efficient and physically realistic.
My work focuses on motion planning, especially when it comes to the environment changes, there are the obstacles coming in and out, or the objects that the robot is trying to pick up and move are moving. And this is especially useful when working with robots that need to be safe around people and other robots.
So the environment may have many different inclined slopes, and this gives rise to a lot of different options of when to play the foot and where to play the foot.
Robots in the real world have to operate in environments where obstacles around them are moving. So whether that's in hospitals where we have people moving around, whether that's in a factory where you have other robots that you might need to avoid. My research interests are in developing algorithms and motion planning software that will allow us to move robots in ways that avoid those obstacles.
I particularly enjoyed working on the large-scale projects which we have within the group and helping with the project management side with the Alan Turing Institute, the ISCF hubs, and also the EU Horizon 2020 projects.
So if you've liked some of the research that you've seen in the video and would like to work on some of these exciting platforms and projects, please do get in touch with us, and we'd love to have you as part of our team. Cool. Okay, thank you very much. I'm sorry I've run over time, but I'm sorry about that.
Thank you very much. The robot cafe is actually just a few blocks away from here, so 15 minutes walk from here. So, okay, so any question? Yes.
I will join your lab soon. It's very inspirational. I was wondering about the learning and the representation part.
Yeah.
It just makes sense.
Yeah.
Everything that you said. But I was wondering if you have thought about learning representation during learning, rather than like hard coding these things. And yeah, even if it is hard coded, like trying to understand how to use that.
So we had a whole EU project on that. It was called TOMSY. You can look it up, TOMSY, with Danica Krajcik in ETH and a bunch of other really good people. That was about 5 years ago, where we exactly tried doing that. We tried to learn the representations from scratch. What we figured was that for these kind of complex problems, that is too ill-defined. So if you don't have some structure, some sort of parametric choice, so in the end, the compromise we ended up having was we gave some candidate set of representations, and initially we thought we could learn the weights, but even that didn't work. So you have to make a binary or a sparse decision about what is a good representation to work with. So it is a dream, yet a dream of mine. I mean, I saw your presentation yesterday about learning new predicates, right? But we haven't been able to do that for robots.
A very wonderful work.
Thank you.
And it's very exciting. I just see the topological precision is a very effective way to handle in the relation program.
Yes.
Yeah, but I guess the relational reasoning when the environment changes still requires some time. Well, we see some video of Boston Dynamics. Their response action is very fast. Does that mean they have a speed up issue or something programmed?
Yeah, so the Boston Dynamics videos, so they have got amazing hardware in the sense that you can do very, very dynamic motions. It's very fast, its reaction very fast. The only minus side to it is that most of these actions, so there are some reactive behaviors that are pre-planned. For example, the center of mass adjustments, there are some pre-programmed ways of adjusting the center of mass in response to some instability. But everything else, in terms of the motion, high-level motion plans, in terms of is all fully canned. So when you see them jump over tables and stuff, that is 100% fully known environment planning that happens ahead of time, and then fast local MPC adjustments to deal with small slippages and stuff like that. So there is no high-level fast planning that's going on. This one here.
Yeah, this is
interaction mesh. Okay.
Okay. Blue rather than green. So is this idea applied to generally to the entire design robots? I mean, this would reduce the degrees of freedom of the motions, and that would reduce the number of parameters to learn.
No, opposite. It increases the degrees of freedom. So actually, compared to the number of joints, because you need interaction mesh from many points to many points, the space, the degrees of freedom actually increases. So it is not a method of reducing the degrees of freedom. It's a method of planning. So it's a high dimensional planning problem, yet it avoids the sort of the space in which the plan ends up in is high dimensional but very nice. You can do big jumps in your gradients in the plan without worrying about getting stuck in local minima. Things like that.
You might want to compare this with the idea of, Russian physiologist Nikolai
Bernstein, yes, of course. Bernstein's principle of minimum intervention. Yes.
This is contrary to his idea. What
is so Bernstein's principle, so Bernstein's ideas were mostly about idiosyncrasies of movement. So there are all of us, we are very different people, but when we move, we have some very common ways of moving. So his ideas is, why do we move so similarly? And there, the point there is that when we have some very similar kind of energy conservation or some other things, you do not explore, or you do not, the space in which of the motions that you end up having to explore is much narrower than that you think. So Bernstein's principle of minimum intervention is about saying that there are some bits of the tasks where you are extremely idiosyncratic, and there are other parts of the task where you got high variability. And there is a natural transition between this high variability and low variability. But this has got nothing to do with the actual motion. This is only to do with how can I make the space of the planning much more smoother. It is a little bit like support vector machines. You blow up your input into this infinite dimensional or extremely high dimensional space, and then you do some simple linear operations on it. It is not very million miles away from that.
What's the general discussion of the robotic community towards Bernstein's idea?
Oh, I think people do accept it. Even in human motor control, that is exactly what is used to solve redundancy, to do regularization of inverse solutions. They exactly apply the Bernstein solutions. Absolutely.
Let's thank Sethu again.
So today I'm going to talk about learning integral models on complex medical data. So I'm from Northeastern. I'm a professor of the Electrical and Computer Engineering Department and also director of AI faculty for our new Institute for Experiential AI at Northeastern. So before I start, I'd like to give you a bird's eye view of what I do for research and in general, the type of what kind of research that I work on. So first of all, I do foundations in machine learning, but also I like working on applications, how machine learning can make impact in health, science, and engineering. And I like working on multidisciplinary domains because it also pushes the state of the art in machine learning. So it helps both fields together. And as you can see, throughout the years, I have built several collaborators and worked on multiple domains, and from skin cancer diagnosis. So this is one of my oldest collaborations. So this is with Sloan Kettering Cancer Center. I work closely with an optical engineer who builds confocal microscopes, and it allows you to see under the skin. And we develop new machine learning and image processing algorithms to help them see under the skin and help guide and also have better diagnosis of skin cancer as well, and also better treatment of skin cancer. And let me just go clockwise. I've also developed collaborations with climate science, and it's very inspiring, but it's also very challenging because they have really dynamical models, and also they have very large data as well. And here, the part of work that we contribute is basically, we have these global climate models, but they are at coarse resolution scale, and we try to help better predictions at a local scale so that we can inform policymakers on what to do on a smaller scale. I've also collaborated with radio signal detection and also a lot of other medical applications such as eye disease called retinopathy of prematurity. Working with psychologists to understand emotion and also brain is also interesting, and we're helping them learn about individual differences of emotion as well. And working with collaborators, looking at the impact of environment and toxicity levels in water and how it impacts preterm birth. So, and finally, I also have collaborators with Brigham and Women's Hospital to understand a disease called COPD, and you'll hear more about this. So working on real-world applications allow me to make impact as well in advanced state-of-the-art in machine learning. So for example, you've probably seen some of our work on unsupervised learning and dimension reduction and feature selection. And now we're working more on interpretable and explainable AI, which is really related to these concepts. And also working with domain experts. We know that not all of them are equal. So we also develop methods where what if you have multiple uncertain experts, how do you figure out and learn from them as well, and figure out who to leverage to learn the uncertainty of the experts as well, and learn battle models from it. And then similarly, getting labels is expensive, so we also develop techniques to do intelligent labeling, which is active learning, and also as we know, optimizing hyperparameter tuning is not easy, so we also develop Bayesian optimization techniques as well. And again, working with real-world applications is really important to leverage domain representations. So we also work on those and develop techniques that allow you to do that. And finally, learning from deep representations and also on robustness. So as I said, working with real-world problems and seeing the advances of machine learning, it's really quite exciting, but also it's very important to make sure that our models are trustworthy. So more recently in our lab, I've been focused on trying to make sure that the algorithms are trustworthy, because I work on domains that are safety critical, such as health and others. So then note that I work on explainable AI interpretability, focused on robustness as well, and inspired from working with data. So, you know, machine learning algorithms, note that it's not static. When you train models and you build a learning algorithm and you deploy it to the world, you see new things. So that's why also our group has started to be interested also in developing new techniques for continual and lifelong learning. So there's so many things. That's why it's so hard to give a short talk. So I'm going to focus on one aspect so that you can see how working on a real world problem inspired our work on interpretable and explainable AI. So let's start with the problem. So what is chronic obstructive pulmonary disease, or COPD? Is a lung disease that is characterized by airflow limitation due to noxious particles such as smoking. And this is a disease that is the third leading cause of death worldwide. So I work closely with Brigham and Women's Hospital and a cohort called COPD Gene, which is a cohort of 21 hospitals across the US. And they've collected lots of data from high resolution CT images, clinical variables of lung function, and also genomics data. So right now, anyone who has difficulty in breathing and who has been smoking for a long time, they just characterize that as one disease called COPD. But doctors know that it's actually a heterogeneous disease. So they want to understand this disease. They want to learn how to stratify them so that we can have better prognosis and treatment of these patients. So they have collected lots of data, and then they came to our group and asked us, can you help us stratify and learn subtypes from these data? So again, what is subtyping? Translating that to machine learning, it's when you hear about it, subtyping is a clustering problem. So what is clustering? It's the process of grouping instances together based on some notion of similarity. But usually, sometimes when working with people who are not in our field, they think it's just magic. So we have to explain that actually, when you use algorithms, they're dependent. What do you mean by similarity, right? And similarity oftentimes is typically in the form of a metric or a probability model. And we have to explain to them that one challenge is that defining this is also the same as finding the right model. And you really have to understand the models that you use when you try to do discovery. So for example, if one uses k-means clustering, it assumes spherical clusters that features that you're using are treated equally. Gaussian mixture model can allow you to find elliptical cluster, hyperellipsoids, and so on. So let's start by trying k-means, for example, or even Gaussian mixture model on this data. Trying it on this data, we find that we're just discovering something that they already know. It just groups together patients based on severity, which they already know, and they actually do better. What they really want to do is try to stratify patients based on progression of disease. Meaning, and also we have features that are not at the same level. We have features called pack years, which are exposure variables. How long has the patient been smoking, and also the age of the patient. So basically those are exposure variables, and we have other features where it's manifestation of the disease. So you can't really treat them equally. So my student who was a physicist has a modeling point, thinks about this as from a modeling point of view, and really want to understand the mechanisms of disease that allows you to learn this progression. But our problem is our data is cross-sectional. There's no time in our data. Luckily though, the cohort tries to collect data, like for NIH funding, is phases of 5 years. So we are at the second phase, so we know we're going to have a second time point, but that's not enough to learn trajectories. So how can you learn a trajectory? So on the right is an example of our data in simplified in 2D. And I put x-axis as age as a surrogate for time or exposure variable, and y is a lung function variable. So really, imagine there's no color because the data is really no color, and you have to learn clusters from here. So we want to learn trajectories of disease. So of course, as a machine learning person, we thought that, wait, well, let's learn this nonlinear functions and then learn clusters of nonlinear functions. So how do you model nonlinear functions? As a probabilistic person, use GPs. So Gaussian processes are really nonlinear, are flexible models that allow you to learn nonlinear functions. And so we use Gaussian processes to model these disease trajectories and then learn to figure out which cluster they belong. So we added a latent variable, a digital process mixture, so that we can also learn how many clusters to find. And finally, even though we only have 2 time points, it's useful because now we can use that also as constraints. Must link and in a semi-supervised learner to at least because it's too flexible to allow our model to make sure that we're learning good trajectories for the patients. So this is an example of the result of this mixture of GP model with constraints, and it allows us to learn trajectories of the disease. And this was quite interesting because it allows us to stratify patients based on how long they have been smoking. And that was something interesting to the doctors, because what they really want to know is that why is it that some patients, even though they have been smoking for a long time, their decline is slower than others. So this is what this model was able to do. And my student was able to publish both in ICML and also this Blue Journal, which is a medical journal, a high impact medical journal for pulmonologists. Okay, now another challenge typically with this problem is that we have high dimensionality. So that picture I was just showing you so that you can visualize. So it was low, but typically our data is really high dimension. So not all features are important. Some may be redundant, some may be irrelevant, and some can misguide the clustering result. Plus, when you have fewer features, it makes the model more interpretable and make it less complex. So we want to do feature selection as well. So luckily, our lab has been doing feature selection for a long time. What my student did was just add the latent variables. So instead of Dirichlet, now we have a dual beta process variable so that we can select which features to pick for each cluster. So this is data and feature matrix, and basically the rectangles are the latent space of which cluster they belong to. Applying that and also this Gaussian process trajectory model allows us to discover the features per cluster and yet also learn trajectories of this disease. So this result, my student did, and again, we published this to KDD. Okay. Another difficulty with unsupervised learning is that really it's a problem where you have a bag of marbles and then someone says, group them. Of course, you can group them in multiple ways. You can group them based on size of the marble or color. So there are many different ways to do that, but how do you do it in an unsupervised way? Similarly, if someone gives you a data set of face images, you can group them based on identity, or you can group them based on pose, and they're all reasonable clustering. So this is a similar problem. I have this data. How do I learn clusters from this data? So I have to figure that out automatically. And so it challenges our group, and then it allows us to also be innovative. And as you can see, we've published multiple papers on this, because typically a problem with unsupervised learning algorithm is that it's just find one clustering solution. So for our group, we started developing methods where you can find multiple alternative clustering solutions that gives you different views of the data, but also important and structured, reveal structured possible groupings. And there's several here because we have several different models. One, the earliest one was based on orthogonal projection techniques, which is linear. Of course, you can extend it to nonlinear with kernels. So we also have a spectral clustering base also related to Hilbert, using Hilbert-Smith independence criterion, which this group likes to do. We also have non-parametric version of this. So we have a variety of model. And this showcases the types of clusters we can discover with multiple alternative clustering run simultaneously on the COPD data. So note that if you just mix all the features, it's very easy to find the structure, but then doing this, learning the actual various views, we learned that you can cluster them based on airway and also based on emphysema, which the doctors actually understand and appreciate. So this is a sample similarity heat map, and note that when you see a block diagonal structure, it means better cluster structure. And these are the features. That's why we know it's an airway disease, and these are the features that are discovered in view 3. That's why we know it's an emphysema disease. Now, another challenge we have is that, okay, for machine learning researchers, this seems like we're making it easier, right? All the feature selection is interpretable. And with the modeling with GPs, I mean, it's interpretable as because we know what the model does. But for the doctors, they still don't understand that. Because really, so in our collaborations, listening to them, we find that when they group patients, it's easy for them to group patients based on rules. They come back to say greater or less than this, greater, and so on for each feature. So they really come back to very simple rules. So we need to talk to their language. So it challenges us and also inspired us to come up with a technique where maybe they trust our method better if we start with existing rules, which they have developed for a long time after years of practice. So these are the kind of rules that they have. And then now that we have a lot of data, can we use the data to adapt these rules? Similar to what Zihua was doing. But we're doing this in a probabilistic way, which is not that easy. So we use these rules as priors, but we want to build rectangular rules. And imagine we want to move the threshold of that rectangles. So my students starting thinking and developing a model that can do that. And we want to disentangle two types of features. One are rule generating features we call X. These are the simple features that we use to bound the rectangles using features that doctors understand. In this case, FEV1 and FVC, which are lung function variables of clinical function. And then we thought that maybe we can guide this also so that we can have more complex model where Y could be maybe that disease trajectory, GP, or it could be supervised, some features that's typically inaccessible during the clustering process, during test time, but you can during learning of models. So for example, the future decline of the patient, Y, or genomic data of the patient, which is more expensive to collect, that may not be often available when you have the patient for classification. So we disentangled two features, rule generating features and cluster preserving features. And my student developed an algorithm we call DREAM, where we have a latent variable that you can learn that is interpretable, rectangles. So rectangles based on X features that are simple, that doctors understand. And then yet be able, once we have that latent space, we need to make sure we have a cluster preserving space. For example, a finite mixture likelihood where Y that preserves Y, that you want to preserve about Y. And so that's the model that my student developed. And the nice thing about this is that we are able to adopt the rules automatically. So these are the existing rules. And from data, this is the adjusted rules that we're able to find. And it did have better p-values. And also we're able to do this adjustable yet understandable. Okay. Now I'm moving on to more modern. Note that these are things we've developed through the collaboration, close collaborations through the years. And now deep learning came, right? So it works well. And also we started working on the gene expression data. So this is very high dimensional data. And the features in deep learning looks like that. It's really very, in gene expression data looks like this. It's very noisy. If you just do unsupervised learning, it's very difficult to figure out how to define that similarity measure, like what features to use and so on, because not all features are important. Instead of being fully unsupervised, we thought, well, in genomic data, it has a lot of information that it carries, but maybe some portion of this, only some portion of this are useful for the task at hand. In our case, COPD, for the disease. So only a few features are important for the disease. So we thought, why don't we guide our feature selection with in a supervised fashion, but using some Y variables that we know are related to COPD, such as smoking and non-smoking. So we started thinking of surrogate variables to guide it. So now this is a feature selection problem. Now let's look at all feature selection methods that exist around this time. Most of them are global. However, we know that feature importance might vary across populations. And the nice thing is that around this time, we're starting to have explainable models in machine learning where we are now as a community looking at which features are important for prediction from a black box. So basically now we're looking at instance-wise features, which features are important per sample. Basically, you can think of it that way. And this is quite useful in our health problem because really for different patients, different features are important that's connected to our disease. And we want to learn that. And also, we want to use this also to group the patients, because if they have the same features that are activated or related to the disease, we want to use that to learn the subtypes of patients that go together. So basically, we want to learn instance-wise features. So we want to learn instance-wise feature selection. Now, another issue with genomics is that multifold features, there are many features, this high dimensional, many of the features are redundant. And when you see feature selection algorithms, for example, like Lasso, it will select features, right? It will select features but throw away equally strong features if one of the features is already selected. So for example, A and B are redundant with each other. If A is selected, it won't select B. But in this case, we actually want to know all the features that are important and which one go together, which one are go together and work together. So it led us to the problem of, can we find instance-wise feature grouping, where for each sample, we know which features are redundant with each other, and these features are also important for predicting Y. And this is per sample. So it led us to this problem. And also, I always find problems and challenges as ways to develop innovation. So our team started developing this method and we published at NERMS. So with this technique, note that picture now looks like this. We're able, white one are the features or the genes that are selected per patient. And interestingly, the genes that were selected per patient for non-smokers are more similar. And then the genes that are selected for smokers were more similar as well. Now, what the method looks like, it's more complicated. Yeah, so the message I'd like to provide also is that you can have a more complicated function. I think of this as function approximator. Yeah, it can be interpretable depending on how you design it. So for this one, basically, we want to find features that are relevant to Y and also group together features that are non-redundant with each other. So again, we introduced a new paradigm for instance-wise feature grouping. Basically, again, we have those features X. We want to find the features that can be grouped together and think of learning a G matrix of indicator variables of which features go together. And also find which groups are important. It's like group lasso. Think of group lasso, but learning the groups. And also this should be instance-wise. So that's what we were trying to do. So instance-wise group lasso that learns the feature groups. We formally define representation redundancy, basically a mutual information between xj, each feature, given a lower dimensional representation z. So basically the indicator matrix gx gives you z. And then now we have a group selector S as well. And finally, we have a prediction model in that lower dimension space to predict your Y. So we have a representation redundant mutual information and a representation and a relevancy redundant mutual information between our lower dimensional representation for each feature xj given a latent space z with our predictor variable Y. So we use this to find our features and prove how these redundancies can be captured and preserved. And again, we use that neural net architecture to do so. And to estimate this mutual information, we use a variational lower bound. And with this, we're able to do instance-wise feature selection and show that our method, the blue curve, is better than competing models. Again, it's easier to see it with images. Other techniques can find pixels that are like scattered throughout. Our method will find features pixels that are grouped together. So for example, the fashion MNIST, it finds all the pixels that are shoe-like, pant and shirt, and similarly for the digits. On the genomic data, what we find is that the features from the smoking related patients end up being related to pathways that emphasizes immunoresponse, which is interesting and made sense. Now we started looking at working on genomic data. Another representation that our doctors are interested is that they're interested in directional interactions between the genes. So a lot of interpretable or explainer models out there, given a black box, only find which features are important. So in our case, we want to extend this and figure out, can we learn interactions of the genes from a black box? And in particular, instead of a symmetric interaction like correlation, we're interested in directional interactions. And I'll explain later why it's important and the information it can provide. So let's start with what we did was extend Shapley. So Shapley is an information theoretic technique for explainable AI on black box models. And the idea is that basically it checks each feature and see the marginal contribution of the feature. So here, basically this is the utility or the value of the feature. And basically S is given subset S, look at all the subsets S, how much contribution is feature I provide more than if I didn't have I in that subset S for all subsets, for all 2 to the D subsets for a D-dimensional feature space. So that's what univariate Shapley does. Now to extend this to interaction, to bivariate Shapley, what we did was simply change S here to look at subsets that include feature J. So given that feature J already exists, how much contribution does I have given that J already exists in my subset? So that gives us directionality of how much more does one additional feature provide given an existing feature in the set. So this gives us bivariate Shapley. And note that you can actually extend this to higher dimensional interactions. We just put that in the supplement rather than the main text because it's difficult to validate higher dimensional, but you can imagine you can have higher dimensional and now represent that as a tensor. Here for bivariate, we represent the directions as a graph and as a matrix. So how much more can you get from here? So this is feature importance, univariate on text because sentences are easier to understand. So on text data and where the prediction is sentiment, note that features words worse, surprising, and awful were considered important. But the bivariate interaction gives you something more information that you can get out of this. So here it shows that if I know worse, I've seen worse, I don't need surprising anymore to know that it's a negative sentiment. And that's what the directional arrow provides. If I have awful, I don't need surprising. So we call that directional redundancy. So awful makes everything that points to it redundant. Now another concept we can find from this directional graph is mutual redundancy. When there's no edge between these two features, they're mutually redundant. So in this case, awful, if I have awful, I don't need worse to know that it's already a negative sentiment. So it can discover that kind of relationship. In addition to which features are important, you get the univariate information also freely when you do this bivariate chat. And then here are the results. It shows that, again, in machine learning papers, we always show that we're better than competing models. So that's all that you can get from there. And finally, I just want to show another way where you can provide domain guidance to interpretability. So here, this is another application area on images, on the retina images. This is an attention model without guidance. It just highlights everything that's important. And it's not that meaningful to our doctor collaborators. And in the past, when we did classification models, we usually extract important features and then do classification. So in the past, we know that working with our doctors, that wiggliness or tortuosity features are important for disease. And it's easier for them to understand. So what we did was guide our attention model by looking at tortuosity features and add this to our loss function. By adding that, we have a smarter or more interpretable understanding of which part of the image is actually important for making the decision. And also it gives us higher predictive performance as well. Okay. So I'd like to end by saying that when you work with real world problems and working with domain experts trying to understand data, you'll find that it's really important to make it interpretable. And interpretability elicits trust. And this is quite important right now because a lot of our models are performing really well, but we don't understand what's going on. So for our group, it's very important for us to make models interpretable to our collaborators. And key to it would be considered, it's really a communication. When you're trying to make things interpretable, it's trying to communicate what it's doing. So consider the human that you're trying to communicate the result to. Use the language of the domain. And of course, visualization and summarization help. So I'd like to just thank the students who worked on this and my current lab. By the way, because I didn't have time, and I know a lot of you are working on continual learning, I also added just a slide showing that a plug on some work that the student did. So thank you.
Okay, thank you very much.
Any question?
Yeah.
Jennifer, thanks for the excellent work. So I had a question on your the models where you did the pairwise.
The bivariate chap,
Bivariate chap, yeah. I'm curious about the relationship of this kind of work to, say, graph cut in conditional random fields, and where you use higher order correlations in, say, vision grouping. Any thoughts on those conditional random fields?
For conditional, it's undirected. This is directed, for one. Yeah, and we are trying to discover the direction, the edges. This one we're trying to discover the edges. So you're given a block box, let's say a deep neural net, and we're trying to interpret which features interact, which features are. If I'm given feature 1, I don't need feature. Do I need feature 2 or not to predict why? So we are building an interaction network like that.
Okay, so in your case, that directionality matters.
Directionality matters, yes. Yeah.
So if we talk about interpretability, then large language models, of course, appears in some context. So I want to hear your opinion whether that have negative impact or positive impact to this kind of research.
Large language models. Maybe instead of large language models, transformers in general. Well, they work really well, right? So for example, for transformers, for genomic data is also working really well on genomic data, and then on images, vision transformers. So what our team will be trying to do then will be, given that black box, what is it doing? How can we make that interpretable? So a lot of these techniques you can still apply to that black box and figure out which features are important, because it's still just a function approximator. So we can do that. And what I would say is that it's just our attempt to make it more transparent, but there's still a lot of work to be done. And I think transformers are quite interesting too. Yeah.
So
to figure out why it works.
Also interested in analyzing the behavior of transformer mathematically.
Mathematically.
Like transformers are kind of looking like giving some nice interpretation intuitively, but in practice, it's really a black box.
It's really a black box. We still have to figure out, and as a community who are developing methods, this is a challenge. Every time I see challenge, again, I say it's an opportunity to come up with novel ideas. So for us, our challenge would be unbox it. And yeah.
The questions?
Regarding the bivariate sharply interpretable, so I think one thing, can you give us one practical application when the doctor needs such interpretable? Like given a condition, one feature, what other importance of other features?
What they really wants to know, so it's the genomic data. They want to learn the pathways, like which gene affect the next one, and but we only have like a black box predictor. What can we get out of this? Can we learn those connections? And we're just starting with this interaction connection first, and it's actually a step better than what exists now, because what exists now they usually just use correlation. So this is a step better. And furthermore, what we're doing too is we're learning, again, this is instance wise. We're learning how features interact instance wise. And I'm hoping how we can use this, again, related to the subtyping problem. Now we can cluster this networks. So which patients are more similar because they have the same interaction. I don't know if that answers your question.
Yeah. Thank you. By the way, on the other hand, the computation has been quadratic.
Yes, it's more yeah. The computation is more challenging.
So another question is, most interpretable method is to relate to the original data space features. What do you think if we need to interpretable the black box internal representations?
The
latent space.
I would go back to it again, depends on the domain. Sometimes the latent space is important because, for example, here, really, I mean, yeah, this is still the feature space because it's easier for us to understand. But if you're interested in the latent space, maybe you can maybe constrain it to be similar to high-level features that the domain is interested in. I would say one can approach it that way. Yeah. Yes.
I wanted to see the continual learning one. Could you say a few words about it?
Oh, the continue. Yeah, I know, but the slides are so tiny. So actually, we started working on this domain because my student was working on the radio frequency problem, and we initially started with our goal was to detect devices, and there were thousands of devices, but then we have to deploy to the field where we might see new devices. So again, now it's a continual learning problem, and in particular, the continual learning problem that we were tasked is really given a good trained model, can you learn new classes that you haven't seen before that was not in your training set? So it's an open set semi-supervised learning problem. So so here at stage 1, this is a deep neural net, and then really what's important is the latent space. So I think of deep neural net really is like it's an end-to-end method, right? But then what's happening is that you have a feature extractor. So, and then you have a classifier, a linear classifier in the end, the final layer. So what's important is this representation that's learned, this latent space, the hidden layer. So this is the supervised part. And then now, once you deploy to the new set, can I learn new classes? And we use HSIC because I like HSIC with latent spaces, such that you want the supervised part to match to the things you know, and yet also learn a latent space that is a good representation of the unsupervised new data. So that's the semi-supervised formulation we did, but through latent space. And then now, so that we can discover new data, new classes, we did clustering to discover new classes. And then we train a neural net for an open world semi-supervised method. So this is one of the earlier paper in 2020, which was published in ICDM. We also had this same cool idea where in continual learning, the issue is that when you learn a model and you adapt to new things, you might forget the things that was already trained before. What we did was, what we did was learn, and then what if you also have limited memory space? So what we did was learn, and then we prune for task 1. And then as I see new data, you learn again for task 2 and prune, and then also figure out what to share together. So we called it a learn, prune, share algorithm. And the nice thing about this, we collaborate with someone who's an expert on compression of neural nets. That's why we have this like an optimization formulation of continual learning. And I think this one might be what MT is more interested in. This is one of the earlier version of continual learning. I had a postdoc, Ting Ting. She was actually Alex's PhD student, and so we had a Bayesian approach. So we have a variational autoencoder. So one of the nice thing about unsupervised continual learning, so we were tackling an unsupervised continual learning, where can you learn new classes in an unsupervised fashion as you see more data, new data. And Bayesian is a really nice way of allowing you to just update the posterior. So that's what we did. So we have a variational autoencoder. Again, the key is the latent space. You have a lower dimensional space, but to allow us to learn new classes, we have this Dirichlet process mixture so that it's not parametric and to grow new classes. To allow not forgetting things, we built what we did was she used the sufficient statistic of the learned model so that we can use that to replay things as you train to the new tasks, as you see continually. So you just grow and continually do this with a variational mixture autoencoder and replay using sufficient statistic. And finally, a more modern version is using transformers. So this is the latest version. One of the Zifang actually had another one this year, but last year he used transformers with prompting. So the nice thing with prompts is that it allows you to adapt to find context to use. So what he did was learn a pool of prompts, and then a test time, meaning online, it figures out what prompt to use to adapt to the new task. So we don't even need to know what task it is. It also figures out automatically, and it's pretty cool. Like this work has a lot of hits because it works really well. So yeah. So thank you for asking.
One hour lecture more.
Yeah. Yeah.
Okay, so then thanks Jennifer
Thank
for the
you.
great talk.
Thank you.
Professor NODA, to start your presentation.
Okay, so thank you very much for your introduction. So unfortunately, I had a lecture in university, so I must go back to Hokkaido. But I'm very glad to join this event and also activity of evaluation of AIP. Anyway, so today I'd like to present about my work on social simulation. Okay, so this is main topics of this talk, and I mainly talk about the simulation of DRT, as it is a demand responsible transportation. So Uber is one of the famous one, but I like to introduce another type of transportation services. And also, if I have time, so I mention about the pedestrian and the pandemic simulation. So let's go into the first topic. So simulation on demand responsive transportation. So before describing by slide, I like to show some video.
With the recent development of IT environment, improving the convenience of public transportation and securing new means of travel to deal with aging society and rural revitalization are imperative. To solve these social problems, we developed an AI real-time ride-sharing service, SAVS. Public transportation, tourism, distribution, and so on. SAVS uses AI to realize the optimization of the flow of movement in various services. For example, in the AI real-time ride-sharing taxi service, when a passenger makes a request via smartphone app, AI considers the vacant seat in vehicles, calculates the optimum vehicle and its running route in real time, then notifies the passenger and driver of the result. After that, if another person makes a dispatch request, the driving route is altered in real time and the most efficient driving route at that moment is presented. In this way, because the driving route of all vehicles are calculated at the same time, we can realize the most efficient vehicle dispatch throughout an entire city. We also provide demand-responsive services for buses and shuttles. Furthermore, it is possible to create optimum dispatch plans, not only in real time, but also in combination with advanced bookings. Also, we conduct a simulation to measure the effect of introducing SAVS. We visualize the results in graphs or videos and provide them as materials to support making transportation plans. First and last mile transportation, promotion of sightseeing and shopping bags, and daily transportation for the elderly. SAVS can be used in various scenes according to purpose. To realize efficient, safe, and secure transportation citywide, and to improve the quality of services involved in mobility, we invite you to use Smart Access Vehicle Service. Mirai Share.
So in video, the video describe about our service and company, and as shown in the video, so we are providing a service of the mixed style of taxi and bus. And of course, nowadays it is very familiar, but this company is established in 2016. But the research itself started in 2001, so it is very early days, and during the research period, we did several simulation analysis about this kind of transportation system. So I like to describe about such kind of things. So in order to consider about this kind of service, so we try to organize a kind of multi-agent social simulation. So to evaluate the effectivity of traditional style transportation service and also the new style ones. And in the simulation, we use AI as optimizer to reflect a variety of demands. So each people think about the different purpose and different features. And also we use AI to learning to optimize some service system. Using the GA or auction style optimizer and planning methods. And so the simulation itself in the beginning is quite simple. So as shown in this slide in right side, so we consider about a very simple grid style city. And suppose so many people want to move somewhere to another where randomly. And in this situation, so we provide some bus style service or new style ones. And the purpose of the simulation is one purpose is optimization, of course. It is a very simple setup of evaluation. But initially, we focus on not the optimization, but the feasibility of the service. So because in that time, early days of in 2000s, we try to consider new style of transportation, but the issue is such kind of a new style is feasible or it is not sustainable. So in order to answer these questions, so we try to organize the comparison of traditional service and new style one. So, and in that time, we call service style service as on-demand bus service. And we try to compare the case of fixed route, traditional fixed route service and on-demand style one. And we suppose the same condition of demand, and we also set up the same condition of cost. So we introduce the same number of vehicles to operate fixed route or on-demand style one, and then evaluate the efficiency. And we organize several setup of the situation and compare the efficiency of two styles of service. And finally, so we got a very interesting result that shown in the graphs in right side. And this graph show in each graph, so the horizontal axis indicate the number of vehicles to operate the services. And the vertical axis indicate the average traveling time for each passenger. And this means that lower value is good for passenger. So they can reach their destination very early if the value is low. And in this graph, the red thick lines line indicate the case of bus service, the quality of bus service, a fixed route bus service. And in this case, if we can operate the large number of vehicles, then the service quality is improved in a certain ratio. However, if we operate the on-demand style using the same number of vehicles, the speed of improvement if we introduce more vehicles, then the speed of the improvement of on-demand style is faster than a fixed route. So this means that if we can operate enough scale of services, then the service quality is better than a traditional style of bus system. So it is very remarkable result because before our research, most of people in transportation service believe on-demand style is not work well. But this simulation shows there is a possibility to introduce this kind of new things, a new style of services. And so, as I explained, so this result came in very early days of 2000. And in that time, unfortunately, so we have no mobile devices, so no one uses smartphone. And also, it is a little bit difficult to establish some server on internet. And the map service is Google Map also came in on service in that time, but in that time, so most of them think so it is feasible or not. And also, so this kind of simulation or evaluation takes so large number of computational costs, so it is a little bit so expensive. But in 2010, then so fortunately everyone uses smartphone, and cloud service is very common, and also it's a Google Map and other map services is possible and feasible. And also we have many cluster HPC infrastructure. So we found so we can introduce our new idea in real. And so in order to do this, of course, before we establish the company, so we tried operate some experimental service for the participant of a conference. And in that time, so we operate the service in Hakodate, in a city in Hokkaido. And in that time, we did some simulation to determine how many cars we need to provide a good service. And finally, we found so 20 or 30 cars. We need 20 or 30 cars. And actually, so we got a good result from a good response from the users. And finally, so we established the company called Mirai Share in 2016. And now, so we are operating more than 20 services and increasing in Japan. And the scale of our services maybe the 5th in the world. And so at least in Japan, we have most major share in this kind of services. And I like to show some good example about our services. And so this service called KAPI is operated in Kumenancho in Okayama Prefecture. So this is very small town and very mountainside. And they have some trouble because so they have no public transportation in the town. So the town government tried to operate community bus by hand, but it is not so effective. So so they try to contact us, and so we evaluate and design the new style of service. And finally, we can reduce the fleet size and the number of vehicles of the original community bus service. And also, so they operate the manually, so therefore they operate fixed 12 trips per day in fixed hours. But in our system, so we can operate in free time in 8 hours working hours. And so we also provide new features on these services. And fortunately, as a result, so the number of passengers is increased and doubled finally. So the remarkable thing is that this graph shows the number of passengers we bring, and gray one is old style manually operated shuttle bus, and red one is in our systems. And you can see the number of passengers is increasing. And this period start to 2020. It means that the period of COVID-19. So even in that time, so we can get more passengers than the old ones. So it is a very remarkable result. And so this case is very countryside, but our service is not only the rural area, but also we operate the urban area. So, for example, we are operating Maebashi city. It is also a large city in Kanto area, and also we provide this service for tourism. And I like to show as a case of the tourism. So this is a case of Sakai Minato city in Tottori Prefecture. So this is a very small city also, but they have a large port and big cruise ship visit this port, and many foreign traveler want to see many things around this city. And for this city, so we provide our services. And it got a good result, and so many passengers enjoyed the city. So unfortunately, so because of the COVID-19, so this activity become very low in 3 years. But nowadays, the situation is coming back. So we are thinking to restart this kind of activity in Japan. And also, so one of the strengths of our company or service is the skill of simulation, and we evaluate so many data using the simulation. And this is one of the results. And it is a case of the Nagoya city, and we collect the taxi operating data and simulate how many vehicles we can reduce. Reduce, and finally we got so we can reduce 100 or 200 vehicles in a city, and this is most of half of the vehicle in a certain area. And so it is so good for company. Also, it's good for society. In so recent Japanese ones, and it is so so the company is really thinking to introduce our services. And another simulation is that we consider the case more future, and so if we we consider the case, so everyone so no one use a private car, and everyone use our sharing services, and in that case, how many vehicles we need? And we try to simulate this kind of evaluation in the case of Hakodate city. And so Hakodate city has the 200,000 population, and they have more than 100,000 vehicle private cars. And in that area, so we conducted a simulation of our services to transport, to transport residents frequently. And finally, we found maybe 5,000 or 10,000 vehicle is required. And this means that we can reduce more than 10 times of private cars. And so this is also the impact data. And maybe near future, we can get this kind of situation. So anyway, it is one of the power of simulation to predict the futures. Okay, so let's move to another topics. So about the pedestrian simulation. And so we also, I also doing some work on pedestrian simulation or evacuation simulation. And in order to do this, we developed a simulator of pedestrian. So I like to show some demonstration of the simulation. So now, I'm running. This movie shows a simulation of pedestrian. I just stopped the video, and this in this simulation. This simulate the case of people going back to their home from a fire festival held in Kitakyushu. And this fire festival is one of the biggest fire festival in Japan. And many people is watching the fireworks in this area. And most of them return to home using train, and the train station is here. So now, so many people is going back, and green dot indicate the people, and also you can see, you may see red ones, and the color means green is moving smoothly, and red means the people is stopping or slowing down. And now, simulation restart, and now, you see some red area, and this is a kind of control by Gadmans. And Gadmans is trying to keep safety of the movement of many people. And so you can see that many people can enter the station very smoothly. So this is one of the important purpose to design this kind of control. Unfortunately, last year in Korea, we had the trouble in Halloween festival in Seoul. So in Japan, in past, we had the similar trouble, and government and police is very sensitive about this kind of situations, and we are providing this kind of result to government and police department of this city. So it is also the design of the service case. And so the feature of this simulator is also multi-agent feature. So that means that each agent has a very small AI, and we can introduce various kind of purpose and features for each agent. So by this, we can design various kind of simulation of crowd movement. And I like to show another example of evacuation simulation, collaboration with real evacuation drill. So, one of this is a work with Dr. Onishi in AIST, and so we are trying to organize some real evacuation drill with Opera House in Tokyo, and so they organize some very interesting opera concert with evacuation drill, and I'll show some video. So they actually do some opera show, and also in that time, some earthquake. We suppose some earthquake occur, and before the evacuation drill, Onishi-san installed various cameras to record the movement of people. And also we organize some simulation, and audience of this opera is guided to evacuate from the building, and we recorded the movement of people, and also we organize the simulation. And in this simulation, the point is that in the real evacuation drill, we found there are several trouble in the evacuation. So one is someone loses their direction. So they enter the wrong doors, or they follow just people or something. And another trouble is opening the door. So people tend to move toward the opening door, but they never try to open the door. So therefore, if we that only one door is open, everyone rush into this door, but even another door can be available. Is available. And we conducted several cases of the number of opening door and how many people is losing their direction. And finally, we found, okay. We found the simulation result, and this simulation result tells most significant effort is opening the door. So if we can open all doors, we can reduce the evacuation time very significantly. So this tells the staffs of the opera house should focus on opening the door rather than the guiding people. So this is a good lesson. And next year, so we also do the similar evacuation drill in the same theater. And the evacuation time is also reduced so much. So it is the good result from the agent simulation. Okay. And finally, I also mentioned about our pandemic simulation. so this is a simulation in very early stage of COVID-19 pandemic, and it is a work in the first year of COVID-19, so 2020, and so in that time, so I like to know the relation between movements of people and the spread of diseases. And so in order to investigate this kind of relationship, I conducted very simple simulation. And in this simulation, so this is the window of simulation window. And in this map, each green or red or blue dot indicate people, and each of people is moving by random walk in small area. And but in the same time, some of people jump long distance. And so I try to investigate this kind of long jump effect in spread of diseases. And so this is quite a simple simulation, but the result is very interesting. If no one has this graph shows the changes of the number of infected people, and you can see very jaggy lines, many jaggy lines, and but so because this simulation use some random number, so as a process of the spread of diseases is different in each simulation case. So I just show all of simulation run of 100 times. So anyway, so if no one jump a long distance, just go around random walk very locally, then the spread of the disease is not so significant. But if only 1 or 2% of people is jumping, then the situation may change. And if some of people jump long distance, then the speed of spread of the disease is increased so much. So this means that the government should stop some long trip of people. And so I show this result to the government to think their promotion or restriction of the traveling of people. And I do not know this kind of their operation is good or not, but anyway, so at least this simulation tells the detail of the relation of movement and diseases. And so in that process, I also investigate another kind of activity. It is not a simulation, but the big data analysis. And in that time, we got some smartphone data, and this indicates the movement of the people. And so we collect this kind of data and count the number of people in a certain mesh in the map, and classify these numbers by hours and the distance of their home. And so we create three-dimensional tensor using this kind of data. So one dimension indicates a mesh in map, and one dimension is distance from home, and one dimension is house. hours. And we apply some simple non-negative tensor factorization. And finally, we found the 6 factors in this tensor. And we extract 6 types of people's movement. And fortunately, the process of the factorization is quite mathematical, but each of movement indicate the purpose of the people. So one is daily commute to the business office, and another is shopping, and another is leisure. Leisure means traveling and drinking in night. And actually, this is also the factors of map mesh. And actually, in the case of leisure, so we can find some restaurant and bar area in Tokyo. So anyway, this we try to compare this kind of changes of factors through days, and also we compare these factors with reproduction number of the COVID-19, and finally we got this kind of coefficiency. And finally, so we found, as many ones mentioned, so movement of leisure has a significant relation to the reproduction factors. So this is actually, this result support the thinking about policy making, or how to restrict the people's movement. So this is a summary of my talk. So I shows some multi-agent social simulation and its application in public transportation, or pedestrian, or pandemic. And each of them tells that social simulation is a good tool for service design and policy making and understanding social phenomena, and so on. So I hope this kind of technology become more popular in future. Thank you very much for your attention.
Thank you very much. Any questions?
Thanks a lot for the talk. I was wondering how you handle uncertainty in these simulations, and like how do you measure the effect of different kind of uncertainty and still figure out a good cause that shows the pattern.
Okay, so that's a good point. And actually, so the weakness of this kind of social simulation is it is quite difficult to validate the result using the real data. And of course, we are trying to validate using real data. And in the same time, we also do so many simulation in wide range of conditions, and we suppose analysis of wide range of setup will cover the real world in a certain point. And so using this kind of assumption, we will be able to provide reduce the uncertainty of this kind of simulation. So this is our answer to these questions.
Other questions? Yes.
Hello. So I'm very interested in your pandemic simulation things. So because we also did the very similar things and now used by the Hong Kong government to determine their policy in COVID. So I'm wondering, because you're using the random walk to simulate the people's walking, but then the random walking is actually, if you see the distribution, it will immediately convert to 0. So which means that, for example, if you use a random walking to simulate people, you couldn't actually simulate how the people occasionally leave to another place and then to introduce the introduce a new convoy. But in the convoy, it actually is quite common because you can see it always spread in a very distributed way. So I'm wondering, have you determined in your work, do you tell the difference between the random walking, or you are using the levy walking, levy flight, or the things to simulate the random, simulate how people walking? The second thing is how is the government's response to your system? Thank you.
Okay, so I just use the random walk for the simplicity and easy to simulate. And I understand this. So this is this kind of movement is different from the real people's. So and actually, so another my colleague in AIST is also doing some more realistic simulation in a scale of Japan national-wide. So using the full data of mobile phones. But in this case, so we met several difficulty about the data assimilation. But anyway, so useful so more accurate simulation will exist between of this kind of real data simulation and my very simple model. But unfortunately, currently, so the movement of people is not enough to realize the realistic pandemic simulation. So, therefore, I try to keep my simulation quite simple. Keep it simple. And so the last question about the response of the government. And so, of course, so initially the government does not think my result seriously, and they tried to introduce some promotion of the travel. But immediately after, so the pandemic expanded very quickly, so they just stop. And in that time, so they still recognize my result indicates some feature of this kind of pandemic situation. And but because of the simplicity of my simulation, so I cannot extend this kind of things in the direction of more real simulation. And so I just stopped at that time and try to introduce data mining part. So I showed in the last part of this talk. And using unfortunately, in that time I moved to the Hokkaido University, so I just stopped this work in that time. But fortunately and unfortunately, the pandemic may closing now and become a normal situation. So maybe, so I hope we keep this kind of result for the next case. But anyway, so we can start this kind of work more better position in future. It is just my thinking.
Thank you very much for the great talk again.
Thank you very much for giving me a chance to talk about what we are doing at our center at AIST. I used to work for Kyoto University for 15 years and then moved to University of Manchester. Stayed there for 7 years and then came back to Japan and worked for University of Tokyo for 17 years. And then I moved to Microsoft Research and in Beijing and stayed there for 4 years. And I came back to Japan to be a director of AI Research Center of AIST. So before joining AIST, I was really academic researchers and as Sugiyama-san said, heavily involved in natural language processing research. But after joining this center, my role is not research side, more managing and directing the research groups in the center. So today's talk is not really a research talk. So I just want to give a brief introduction what we are doing in our center. So as Sugiyama-san said, the Japanese government thinks that AI is a major source of innovation and quite big impact on industry and also society in general. So the Japanese government established 3 research centers focusing on artificial intelligence. And our center was established 2015 under Ministry of Economy, Trade and Industry. And 1 year later, AIP, this center, was established. And then yesterday, President of TOKUDA talked about activity of NIC. And NIC is under Ministry of Internal Affairs and Communication, also established a research center on AI. So 3 centers belong to different ministries. And because of the nature of ministries, we are a slightly different direction in research. In our center, since we are under Ministry of Economy, Trade and Industry, we are very much involved in deployment of AI technologies to industry and society and so on and so forth. Of course, we do some basic technological research, but we also see the importance of deployment of our technologies. So when we started our center, we saw that 2 trends in the society are very much affect on AI, or AI effect on the 2 major streams of changes in the society. One is society 5.0, which emphasize sort of a smooth transition from real world and cyber world to the real world. And the second trend is revolutionizing scientific and engineering research. We call it 5th paradigm of science and technological research. So simulation-oriented science, computational science is called 3rd paradigm. And then Jim Gray talk about 4th paradigm, which are based on big data. And now we are entering another phase of scientific revolution, that is simulation, machine learning, and big text and knowledge combined. And that gives very different methodologies for scientific research. So we are focusing on two trends in our research center. So the first is a smooth transition of real world and cyber world. So a traditional AI is focusing on internal processing of our brain or in cyberspace. But what makes the current technologies different is development of various very powerful sensors. So we can take data from the real world. And another change is robotics or autonomously behaving agents like a self-driving car and so on and so forth. So the current AI, not only brain, but also eyes and ears, and also hands and legs. So AI is really embedded in the real world. So from taking data and doing some modeling or prediction or whatever, and then that is transferred to the real action in the real world. And also those technologies are supported by the rapid development of supercomputer, especially GPU, specially designed for deep learning type of applications. So this is always at the beginning of our research center. We show this video that is real world is on left-hand side. The robot is moving around, and cyberspace, the robot brain is on the right-hand side, and a robot viewing the environment and modeling the real world in its cyberspace and making some prediction. Like previous speaker talk, the modeling of people's movement and observing how people move one place to the other. And that can be used for prediction of people's movement. And in order to avoid collision with people, the robot plan its action based on the prediction of the people's movement. And in this slide, a blue line is a prediction of the robot. So basically, this is very simple view of a real world and cyberspace. And cyberspace are getting more and more sophisticated, and the prediction techniques are used for much more sophisticated techniques are used for human behavior modeling and so on. But that basic scheme is unchanged. Okay, so I will talk about what we are doing in our center. So our center may be a similar size with AIP, but the configuration of our research teams are somewhat different. We have 13 teams, but the teams are mostly managerial unit, and each team have several PIs in their team. So the number of teams are less than teams or groups in this center, AIP. So for example, 2 teams are mainly concerned with machine learning, some theoretical part, but they are more focusing on a combination of simulation and machine learning and so on. And another group is algorithmic part of machine learning. So 2 teams on machine learning And we have text processing, but we are focusing on non-linguistic data and textual data, how to combine non-linguistic data like observation, numerical data to text. And another team is more focusing on knowledge graph type of technologies and how to combine knowledge graph with text processing or visual processing and so on. And then we have a human modeling team. We put many sensors of a human body, and we have our own human body modeling, like kinetic parameters of human bodies and muscles, skeletons, and so on. And we can make very precise prediction of people's movement. Also, how heavy the workload is to affect human activities and so on. So those are the two groups on human modeling. And then, as I said, we are really interested in applying AI technologies to scientific research. And the two rather powerful teams are involved in bioinformatics and application of AI to biology. And then we have the previous speaker talk about multi-agent simulation, and we have a big simulation of multi-agent models, and also data platform to manage big data, especially stream data, real-time data coming in, and how to manage those big data and build AI applications on that platform. So those two teams are based on that kind of research. And then we have a traditional media-oriented research team, like a speech, and visual processing is quite strong. And also, right now, image processing fields, as well as natural language domain, are the major field where machine learning type of techniques showed its powerful results and so on. So we have three teams, multimodal team, and speech signal processing team, and image processing teams. Both are based on machine learning type of techniques. And also, we think that AI is now a central part of computer science, and also it affects many related domains. So AI is in the center core of information technology in AIST, and we have several different centers which are closely cooperating with us. One is Digital Architecture Center. They are more concerned on supercomputers and application program of supercomputing. And we have a secondment of researchers of our center to this center, and also their center send researchers in our center as well. And the other right-hand side is a robotics center, which are, okay, some of them are basic robotics research, but in these days, a robotics team is also very much focused on AI. So we have a mutual close appointment between our center and robotics center. And then smart sensor type of research team, which is located in different campus, but they are observing human biometric data and so on. So we cooperate with them. And the other is we encourage researchers to have their own startups. So we have several startups. One of them by previous speaker, and also one or two new startups are being planned in this coming year. And then we have a rather close cooperation with Japanese industries like Toyota and NEC and so on, so forth. I talk about a bit more on their activities as well. And recently, in these 2 or 3 years, interdepartmental cooperations have become more and more common. Especially, we are cooperating with the Department of Bioscience and also Department of Material Sciences. And we are cooperating with them as well. Okay, so one is a supercomputer, and our computer is one of our largest computer for AI in Japan now. And for example, this is a bit old data, but when I left Microsoft Beijing, ImageNet classifier to train that classifier takes several days, but now it's a few minutes by using our ABCI and so on. That is quite equivalent to the results of Tencent, Facebook, and Google, and so on. So we are now thinking of using this supercomputer for a ChatGPT type of model. And our current estimation is it would take several days, 3 or 4 days, to train GPT-3 type of language model if we can use the whole our computer and so on. But still, our computer are heavily being used by researchers, especially some of researchers of AIP are also using this ABCI and so on. So we are thinking of enhancing this supercomputer to accommodate big language model as well. And the other is a robotics team. And we have an intelligent robot and also a bio experiment robot. That is really interdepartmental attempt. A robotics group, AI group, and Department of Biology are putting together our effort to develop robots for bioresearch. So this is already shown in some of the presentation yesterday or the day before yesterday, Cancer Research Center in Japan. But the same robot are now scattered all over Japan now. Robot itself are developed by Yasukawa Industry in cooperation with our AIST bioinformatics team. And now this robot is equipped with very high quality microscopic device, and also heavily invested in image processing. And our idea is we observe experiment procedure performed by human, and that observation directly transferred to this robot and so on. So that's quite a successful robot. And like now, about 100 this type of robot are being used in various research institutes in Japan. And our I talk about some examples of our center, but we think the AI is what is like a basic infrastructure and theoretical research, like machine translation and so on. That is a bottom part of this slide. And then top part is deployment of AI technologies in various fields, scientific research and so on and so forth. But in order to link the bottom of research with deployment, there is a rich research field, a more mission-oriented research to integrate different types of AI technologies into one and try to find new problems to be solved in the theoretical groups and so on and so forth. So we think that that middle layer we are focusing as a center. Okay, so we said that three pillars of our research. One is AI engineering type of research, easy to construct AI system. And another one is human and AI, how we can cooperate with each other, or how human knowledge can be embedded in AI system. And the third one is trustworthy techniques and guidelines and so on. So a cooperation of AI is a very simple cooperation, is a robot and human beings share in the same physical space to work together. So a robot can also observe human movement, and also human can talk to the robot, and AI and robot really to cooperate, co-work together. So, okay, that's an idea, but it's very difficult problem. But again, the same picture, that means right up part is a real world, and left lower is a cyberspace. That means the mind of a robot. Robot see the whole environment in his own mind. Okay, but that is a conceptual video, but we are doing actual research, cooperating with various research groups, like Ogata-san of Waseda, and some Osaka University, and our robotics team, and human observation teams, and so on together. And the basic idea is a robot and help heavy task, which is performed by human. So the whole system are controlled by sort of third system, and the robot is really try to help if a human are getting tired and want to lift heavy materials, and robot to help. And that is we construct the experiment venue and try to implement actual system. And the first result show that efficiency and effectiveness are actually improved by coordinating the works by human and so on. The other is explainability of image processing. That is people are quite heavily involved in explainability problem in many research institutes. We are the same. And we try to features which are relevant to a certain diagnosis, and that is shown by human, and the human can understand which part and which features AI use. And also, if some features which may not be relevant by human judgment, that part is removed from the classifier. And what is now we are challenging now is we try to link those phenotypes of observations with epigenetic data and progress of disease of that patient and another type of data. And we're cooperating with Nagasaki Hospital, and we are making image data, epigenetic data, and sort of a progress of that patient, and also effectiveness of certain treatment and so on. So we try to build up we call it multimodal. That means different facets of data are integrated into one database, and try to link result of image processing with more mechanistic understanding of biological phenomena. And that kind of scientists and AI researchers are cooperating to build a new type of research. So these are some of the examples recently announced by other groups like DeepMind, and a lot of other teams are doing a similar thing. So we are also interested in physics-informed machine learning or deep learning system. So that kind of conception actually built by our system, which predict physical parameters of certain chemical compounds. And the simple method is we can accumulate the data like chemical formula and the physical parameters and so on, and train deep neural network. But this work to a certain extent if chemical material is low complexity. But if we go to high mass molecule, then data becomes very sparse, and there are lots of errors actually. So this is the current, not current results. The blue line shows that simple neural network trained by the current available data works quite well in low, how do you call it? Small molecule chemical materials. But that cannot extrapolate to the higher, much bigger chemical compounds. So obviously, we cannot extrapolate the learning results. So what we are doing is to embed some physical physics, quantum physics knowledge in the deep neural network, and try to combine, divide a neural network into two small neural network, and then the result shows this red line is the current our system. That means our learning results have some extrapolatable facilities and so on. So that's quite interesting, and we are pursuing more precise physical model to be embedded in neural network. And that is a close cooperation with material engineering section of AIST. And the other is that are foundation model type of research. So that large language model is sort of one foundation model for language, but the same idea can be applied to many other modality of information. So actually we started that kind of research well before, like 5 years ago, and try to make a foundation model for image processing. And what we are doing is if we have ImageNet trained system, and then we can fine tune that foundation model to a specific application. But foundation model by using natural image may not so effective for example, medical image processing, like how we call it, that stomach image and bladder's image and so on. So we try to fine tune by using rather big data like stomach images first, and then fine tune again by using much smaller data like an image of bladders and so on. And in that way, we can show how the performance is quite highly improved. And actually this actual system commercialized now by private company and embedded in a sort of device. Okay, so we saw that, okay, that foundation model is very nice, but obviously there are lots of problems of foundation model, like a large language model, a copyright problem, privacy, and confidential data, and so on. And the ImageNet have the same problems. ImageNet is fine, but since we use natural image, there is a problem of IP and also privacy problems and so on. So what we are doing is completely different. We use artificially generated image, but not like ImageNet, like 10 million images. But our case is 100 million images artificially generated. Because it's artificially generated, we can generate images as much as possible by using fractal functions. And the obvious question is whether those artificially generated images can be used for building foundation model and fine tune for actual problem solving, like medical image processing or like an ImageNet classifier and so on. And actually it works. That means if we generate 100 million artificially generated images, and then the foundation model are really more effective than foundation model constructed by ImageNet. So that's a quite nice results. And we try to apply the same conception of idea to different types of images, like videos and so on. So that's kind of research we are now focusing. I don't have much time, but one is another is a data platform. Geospatial database can be used many different applications, like a multi-agent simulation of big towns, or Japanese in Japan, that the movement of people or even satellite image processing. And nowadays, satellite image processing are very useful for many purposes. Disaster prevention type of research, or agriculture, or deforestation of certain areas, and so on. So we are cooperating with JAXA, Japanese Space Agency, and put all the data in our geospatial database. And it's easy to say building big database, but actually satellite data and so on, there are lots of work should be done for calibrating or standardizing those images. So now we are cleansing that satellite image and use, for example, solar panel detection and so on, all over the world. That is one. And the other is the same geospatial database can be used for navigation, self-navigating robot. But in this robot, use much more richer sensor information embedded in the environment. So the robot can see which our eyes cannot see. So a robot can see this part of our venue are very crowded. So in order to move from one place to the other, that crowded part have to be avoided and so on. So that's the next step of self-navigating robot. And this kind of robot is now being deployed in carrying patient from a train station to the hospital and in the real world. And lots of people are moving around and so on. Okay, so I skipped several things, but one is, for example, this is plant control, which is combination of simulator and sensoring data, and also reinforcement learning type of techniques. And chemical plant are somewhat sensitive to the outer world. So if a heavy rain comes, the temperature drop. So the state of chemical plant change. So that people have to adjust several parameters to stabilize, or the configuration of oil changed. Then sort of plant is again unstable and make it safe. So we can, till now, skilled operators are adjusting all the parameters and so on. So we want to do it by using reinforcement learning and simulator, and also multiple sensor information. And that is joint work with NEC and Mitsui Chemical Plant and our machine learning group as well. Okay, so conclusions. AI now is becoming more and more deep science. So you cannot solve by single person. Let's say like ChatGPT, you see the authors is 400, or AlphaFold, you see 20 or 30 co-authors involved. So some parts of AI need human resources, computational resources, data resources, and a clever mind. And we want to construct international network to cooperate to do such kind of big science, AI as a big science. And also, we are, as yesterday's meeting, Gonogami-san said, we are very much interested in cooperating with your center and center in NICT and other players in the world, and also domestic universities in Japan. So I hope my talk is okay. We have some cooperation among researchers level, so we want to make our cooperation much more systematic in coming years. So thank you very much.
Thank you very much for the great overview. Any question?
Thank you very much for a very nice presentation. I would like to ask a question about your human augmentation cost center. Would there be a space for dementia or aging research also, or like dementia or aging research in your human augmentation center?
Okay, that's a big topic, yes. And elderly care is one of major topics that this center is focusing. And also, as I said, our research institute encourage interdepartmental cooperation. And just last year, we started new initiative of interdepartmental activities, which are focusing on health and dementia prevention or dementia detection is one of the major topics for us.
Thank you very much. Very interesting.
Other questions? I have a question about the foundation model. So you said you fine-tune the foundation model, adding some medical image to the soul. Yeah. But without knowing the original foundation model, how can you fine-tune the system?
Fine-tuning is a really supervised learning. So our foundation model is here, and then we have stomach image and the classification results are annotated by human, and we just find definement. Okay.
So basically, in that case, you have the model at hand.
Yeah. Okay, there is a foundation model, two different streams. One is a BAT type of foundation model, and our foundation model is similar. That means a foundation model, and on top, there is a smaller neural network attached. And the bottom foundation model plays a role of feature extractor, basically. And then top part is a classifier. And that classifier's results are fed back to the parameters of foundation model as well. So that is a fine-tuning model. So ChatGPT type are quite different, but our foundation model offers that BAT type of foundation.
I see. Thank you very much. Any other questions? Otherwise, please join me to thank Dr. TSUJII again.
Okay. So first of all, thank you very much. Thank you very much for inviting me and for the great pleasure to be able to visit Japan again. And it's the second time this year. It's like Sethu, I never say no when it comes to coming to Japan. And it's particularly nice to be in RIKEN again at AIP. And, you know, just to say that, because you don't hear this, so this has been fantastic for us as the AC, seeing your great work, and of course the great work of Masashi as a leader. But this is really fantastic, and it's a world-leading center, and so I'm very privileged to be able to be here. Right. So today I would like to talk a bit about machine learning for the sciences. And unfortunately, through the discussions that we had, I had to add lots of slides, so I will go over time. So it's like in these modern theater pieces where, you know, you can this ends when either the audience has left or the actor, so you can decide upon this. So yeah, a lot of people have contributed, and you know, now comes my shameless self-advertisement. I'm running this BIFOLD center in Berlin together with Volker Markel. It's an AI center, it's a national AI center, one of 5 in Germany, the biggest. And it consists of the 2 technical components of AI, which is big data and also machine learning. So some of you who have been working with large data amounts, then you know Apache Flink probably. That comes from us, in fact, from Volker. Okay, so, and he just got an ACM award for that. Okay, but I'm not going to talk about this. But we are very interested in exchange, right? And getting new talented people. And so, you know, we're there. Berlin is nice. Just visit, yeah, give a talk. And we anyway have a memorandum of understanding. So we are one of the links that AIP has to the world. One, you know, occasion that we had was that we signed this memorandum with the presence of the German ambassador here in Hiro, I believe. Anyway, so I will first talk a bit about XAI, explainable AI, and then I thought about it for a long time what I want to talk about, and most people have heard me talk about many things, but not about pathology. And this has been something that I've been very interested in for the last 10 years. And I'll tell you about it a bit. And then I will briefly touch about higher order XAI techniques, but also some crazy applications that I'm interested in. Okay, so here's the paper that I will be talking about, among many things. And it's joint work together with a pathologist. He's the chief pathologist in Munich, in the LMU, Frederick Klauschen, and he's a physicist and an MD. So it's a very rare combination, which allows us to, you know, to talk math, which is, you know, very essential for these kind of projects. So just to give you a bit of a context. So a bit more than 10 years ago, the husband of my sister deceased from cancer, and he was a wonderful person. And I was very sad, and at the same time I was foamingly mad. And I said, I have to have my vendetta to this, right? And then just very briefly after I took this decision, Frederick came back from NIH because he was in the US for a while, and came back to Berlin. He was a professor there, and we started talking. And then, so the idea that he had was to have a master student do the following project. So, you know, you have these pathological slices and you classify them into, you know, cancer and non-cancer parts. Now, this is difficult for many reasons. First of all, it's one of these problems where you don't have much data. Second, there's so much variability that it drives you nuts. And third, it takes time. So, and perhaps to give you an impression, I think we took about 7 years to get the paper published because we were way ahead of our times, and you will see why. But the first aspect of this was when we showed to him that this classification works. And just another remark for those of you who don't know pathological slices. So typically you have about 200,000 times 150,000 pixels in one slice. So it's huge. So it's, imagine how many 2000 by 2000 tiles you can cut from this. It's amazing. So you know, the clinics that systematically digitize these amounts, they have unbelievable amounts of data, right? Even though, you know, they don't have so many slices. But again, we classified this, and then it was actually a postdoc of mine, Alex Binder, who was working on this, very experienced guy. And we showed this to Frederick, said, yeah, we can do a classification rate of something, whatever, right? 90 something. So we were quite proud of ourselves. And then he said, boring, or not useful. He didn't find it boring, actually, but it was a bit, you know, he said, this is not what we need, right? So it's clear that you can classify this somehow, but how about telling me why your model actually classifies in that particular way? And then we thought, oh, there's nothing available for that. And we spent some time inventing this together. And this is how layer-wise relevance propagation came into place. And I would just talk detour on that, because the original motivation was this cancer project, and the layer-wise relevance propagation came 2015. So it's actually, maybe the project took more than 7 years to actually get published, but I mean, that's, so you had to do some things on the way. So the reason why I'm telling you this is that there was a serious problem, which is the cancer diagnosis. And there was parts in the machine learning business missing. And so that was a challenge, and we had to develop this. So because that time, you know, you would have a model, whatever, pre-trained, God knows, you just have your model. It's a nonlinear, what's deep one. And, you know, for example, in computer vision, it's very good at doing things like classifying roosters or other unholy things. So then the question is, what makes this model believe that this is a rooster, and this is a novel rooster, it has never seen that rooster. And you have to put this nonlinearity upside down. And that's a mathematical problem that was not solved. And the paper where we, you know, in length analyzed this mathematically, this was the original layer-wise relevance propagation paper, which is quite a popular one, and a lot of people have been adopting the usage of LRP. So what we could do is then go backwards through the model to the feature space, whatever that is. It could be also, you know, a representation layer somewhere, but you know, in that moment we went to the original features, which are the pixels. And then we can color and give the probabilities for these pixels to be relevant for the decision making that model, that trained model has. Okay. So it's clear in this case, this model thinks this is a rooster because of the rooster's comb. And one important thing, because we know that from machine learning, feature selection has been around for, you know, decades, as long as I can think of. So what's the difference? The difference is that we are looking at single image, in this case, single image, single instances. And this is exactly what we have in the medical diagnosis case. So if you are an FDA, you consider the whole population, right? If you are a single patient, you would like your case to be classified and diagnosed well, and you couldn't care less about somebody else with that disease. So therefore, you need the single decision-making explained. And so layer-wise relevance propagation actually propagates the relevance for decision-making backwards through the models. And in the beginning, we didn't theoretically understand this fully, but we have developed a theory in between their proofs, there's optimality, and so on. So, and depending on whether you have max pooling or conv layers or transformers or LSTMs or God knows what, you have to use the right LRP rule that is consistent with that theory, and then this will work. And so there's now tools and software packages like Investigate or Zenit that you can use, and it's useful for people. Okay, so far so good, but when people apply LRP, then they often apply the dumbest first rule that we ever wrote in the paper, which is like sending your grandmother into a race with Usain Bolt, right? Because the most recent methods are of course much better. So you have to choose the right LRP rule, and that can be done. So that has then be applied to graph neural nets, conv nets, to well, we've been talking about this, to gate classification, so to time series, to regression, to unsupervised learning, higher order models, and I don't have the time to cover that.
Can I ask a question?
Yes, please.
All right, I know nobody's asking questions in between, but you're saying that for a single test case, it doesn't matter what happens to others. But actually, if you go to the doctor and you ask them, they'll say, in patients like this, usually we have this kind of thing.
That's right. That's the doctor's perspective. I'm talking about the patient's perspective. So the patient wants the own case to be done right.
So like if you see a rooster, you say, oh, well, the model thinks that it's the red thing. And then the natural question is, why does the model think that that red thing at the top of the head is important? Because
that's another question. So that's the question of what is the underlying higher order concept behind that. So that's already going towards semantic. But let's I understand what you're saying, right? But I think I take this metaphor of a patient because say there's breast cancer, right? So these have many different variants, and so many different positions and many different stages. So for a particular patient, it's important to understand that particular breast cancer case, what stage, what grading, and so on and so forth. So that's what the point that I make. So thank you for allowing me to clarify. So that there's a book on this. It's popular, but we have a second book as well, and we have analyzed. Oh, interesting. So we have analyzed many models with this LRP, and we have coined the term clever Hans strategies. And basically we come up with the insight that a lot of models that are out there, also a lot of models that are seemingly behaving very well, classifying extremely well, are using some artifactual correlations in the data set in order to make their decision. And one of the nice examples that we have is this particular case from Pascal VOC, which is a very old data set. It's going back into the Stone Ages of computer vision, but Pascal VOC has served for about 10 years for the computer vision community. And there was there's horses versus roosters and cats and dogs and whatnot. And the interesting thing that people didn't realize, or most people didn't realize in the first place, was that in the horse class, some of these pictures, in fact, something a bit less than 50%, contained a copyright tag. So it says Pferdefotos.de Lothar Lenz, who's a photographer, so Lothar Lenz left his copyright tag there. And what many models do is the thing that you observe here. They actually don't look at the object, but they look at the copyright tag, right? So that's the clever Hans effect, and a lot of these models are behaving like that. And if you don't have the tag, then the model doesn't know that this is a horse. But if you put a tag next to a Ferrari, just for the fun of it, that's also a horse, right? Okay, so that's coming back to pathology. So after some years of developing this, we now have the technique. Okay, so then we can not only classify, right, but we can also have a heat map. Okay, so then let's look at the details. This is a pathological slice, and this is the heat map, and this is an overlay. And if you're a pathologist, then you can see that there's some things that you know, the red spots are the cancerous cells. So that makes sense from the biological side. But of course, if you would look more to more than of these slices, it's not only the cells, but sometimes the stroma, sometimes it's some, you know, a fraction of lymphocytes and so on and so forth. So there's variations to that, but the model gets it. So, which now gives us the nice situation that we have the data. We can now classify cancer, non-cancer, stroma, lymphocytes, cell types, whatever, and we get the explanation.
Sorry, Klaus. So do you get this at every layers? This relevance thing? You're showing
Yes.
only at the input layer.
Yes.
You get it at every layer. Yeah?
You get that at every layer, so you can also look at abstractions, which is interesting and sometimes very useful. So in fact, it's also, I'm talking now about pathology, but if you ask me that question, I can also say, well, if we want to understand deep learning and the representations, then we can actually use that techniques to see progressively what the representations do. Okay, and we've done that, and there's papers about it. But coming back to this pathology case, in the case of, you know, the slices, it's clear that you can classify that. It's clear pathologists can see that, and that's what they are paid for. And they are paid for the rare cases. They're paid to see the rare cases, not the common ones that you can also see, you know. What we became a bit adventurous, and that's why people took a while to get their heads around to accept our paper. So now we take the pictures, and for some of these slices, we actually, you know, have the molecular expressions, so protein expressions, somatic mutations, copy number variations, and so on, which is one number for the whole slice. Okay, and now we can solve classification problems to all these 60,000 numbers that we have. So, and you could just to give you a context, say, if you have an overexpressed growth factor, it means that something can grow too much, which is, you know, obviously related to cancer, right? So that has to do with cancer. It's a no-brainer, right? So, but a lot of these other things, we have no idea whether this has anything to do with cancer, or we certainly know that it has nothing to do with cancer. So we can now make this classification or regression, and the model, like in most biological models, most biological data can do most of the time random, and sometimes 70% if you're lucky, 75, okay? But now we can look at the heat maps. And that's interesting because we can now study for those cases that can be classified. We can look at what is the biological reason, where is that in terms of the histopathology. And then we can relate this to the literature. And you can find that in many cases you have, you know, 30, 50, 100, you know, of these protein expressions, somatic mutations, and so on, that can be predicted. And Some of them are known in the literature, but many not. So we can check them, we can build a data-driven hypothesis, and then we can go to the lab and test this. Okay. So now we can make these nice, make these nice pictures where we show basically what is the heat map for carcinoma, what is the heat map for tumor infiltrating lymphocytes, what's the heat map for the molecular property. And so that was what we submitted, and then everybody said, no, you're just a bunch of machine learners, you have no idea, this has no biological meaning, and all the typical arguments that you get. Then we did an experiment where we actually predicted something, got the heat map, and took the slice and did the staining with respect to this molecular marker in order to have the ground truth. And then we sent the paper back and said, well, it looks pretty good, right? So that was this paper. A bit earlier than that, while starting later, came this interesting bit of thing. So we had this paper. This is Science Translational Medicine, and if we think about AI applied in medicine, there's big claims that a couple of years from now, no doctors exist. I mean, some people already predicted this 10 years ago. Anyway, so you actually have a lot of papers. You have 10,000 papers or more. And the question is it really relevant clinically or for the medical context? Or is it just an exercise where some machine learner downloads some data, just puts some number and puts a benchmark, right? So I would claim that the latter is not really scientifically relevant. So the way we address this field and the way I do my vendetta is that I really go all in. I really want to understand cancer. I really want to contribute there. And of course, this is totally futile because I have not 30 years to learn about cancer, but I have become a hobby cancer researcher, at least that far. And so the data that we looked at is a very simple one. It's a very simple question, but clinically relevant. And so the idea here is the following. So we have a patient who has a so-called squamous cell head and neck cancer, gets the cancer removed, goes back home, lives for a while, comes back after 5 years, say, and presents him or herself with a squamous cell lung cancer. And the critical decision that needs to be done by the doctors is whether this is a primary lung cancer. In this case, it can be removed and the person can live until 90, or whether this is a metastasis, in which case there's palliative treatment and the person dies after 2 months or 3. So it's a very significant decision. So if you don't get the decision right and you think that this is a metastasis, but it isn't, then the lung cancer can, at least in some cases, develop metastasis, which brings you again to the few months lived lifetime. So although this
would you know that if you just go back and looked at whether the head and neck is returned?
It's not, the head and neck has not returned. Okay. But it's a squamous cell cancer. So the cancer type, the cancer cell, the microscopic thing looks the same. So from under the microscope, even if you're an experienced pathologist, this is a 50-50 call. This goes to the tumor board, then the tumor board decides upon many aspects that are not histopathology. Okay, so that's the question, and it's not so rare, right? So the tumor origin is uncertain, and then in some cases you can really find this out. So that's the kind of statistics. So now the question is how to solve this problem, and of course we are not solving the problem. We are just taking some technique that is available in biology and applying some machine learning to it. So if we think about all the molecular biology, then you have the chromosome, and then you have the DNA somewhere down the stream, and then what happens during your lifetime and during getting disease and leading a bad life, right? So methylation on the DNA methylation actually is a good record of your sins, right? And so let me see. I will skip this. So if you think about the DNA and methylation, and if there was a way to extract the DNA, the methylated DNA and the positions thereof, and there is, because there's a machine that, where you put in tissue, you get a vector of 800,000 methylated sites, and that costs $300. Okay, so that's a very nice, very practical approach. So then you have a tissue, you have the methylation profile. Okay, so let me, because the sins are a bit metaphorical. So if you're a cell, right, and you develop over time, and maybe you also develop to be a cancer cell. That's in this process, the cell develops some methylation profile, which also basically gives you a record of how the cell developed. And that's exactly what you need when you think about the metastasis, right? Because it would be from a specific different tissue type, namely head and neck cancer, to lung type, but you develop the methylation, on the way there, right? Okay, so what they would be doing is they would get the methylation profiles from that machine, and there would be big data in that case, 1,000 cases. Wow, now that's a lot, right? And because it's not rare. And then you have, the lung cancer squamous cell and the head and neck cancer squamous cell samples and the normal lung cancer. And then you have the validation cohort, and then you could just visualize this with TSUJII just for the heck of it, and you do a classifier training. Of course, what is reasonable is to do a bit of a dimensionality reduction on the way, and there can be some smart informed dimensionality reduction. So then you do a classifier training. So the first thing is random forest. And you can basically see that, imagine the human is 50-50, right? So the random forest can have at a threshold accuracy of 92.5%, which means that it rejects most of the cases, 57% of the cases. So there's 43% predictable cases at that level, right? Then you have a raw accuracy basically of that. Okay, so here's the neural net. It's quite different, right? Because you can basically diagnose 92% of the cases, whereas 8% you can't, right? The model says no, right? So that's quite something, because all of a sudden you have a model that does something meaningful. Of course, it's a model that uses the methylation profile, and the methylation profile is exactly the biological thing that you want to look at. Okay?
It's on like thousands
of
patients. So
yes.
Do you think this is like
p-value?
Yes.
Yes. So you know, the point I think is not that so that the validation part, you know, that's the really left out part. So that's on that, right? But I will tell an anecdote very quickly, because that's the question that you need to ask, right? Because in the end, let's face it, if you want to use this really practically, you need to be sure about it, because otherwise one guy dies from a wrong diagnosis, right? So, but we have the Kaplan-Meier plots, and we can see that if we are, you know, looking at this from, which are basically survival plots, right? Then there's a huge difference that we can achieve. And this is now on 51 cases, okay? And let's talk a bit about these 51 cases. So the data that we trained on was public data, okay? Everybody can access it. The 51 cases were in-house data that were not used in training and not used in validation. They were in some basement, and you know, we got the tissues, did the methylation, and we got also the diagnoses and the profile and the medical records and the diagnosis, the former diagnosis. And then, so it turned out that we got this right in 50 of 51 cases of the in-house data. And so we were quite pleased with that. And I was happy. I thought, okay, that's statistics. You know, you have to have one, this is wrong. And then the doctor said, no, let's look at this, right? This one case. And then, you know, after a while of additional analysis, they found out that this was actually a misdiagnosis, which was interesting, right?
So their system was correct, and they...
No, I mean, this was a human, you know, tumor board kind of misdiagnosis.
But you said in the beginning that there's this 50-50% chance.
Yes.
If you make some decision.
Yes.
How does that come in here?
Well, I mean, these are classical data from the medical school, and where they do the diagnosis as you would do is 50-50 plus the tumor board and plus the additional information that you have.
Okay.
Okay. So it's likely that there are some misdiagnoses. But anyway, so this was interesting because, you know, one of the things that I learned is if you study medical data, you shouldn't trust the usual cross-validation game. Really have to have something independent, a cohort from another clinic or from your own or something. You take public data, but you take something else. So this was very satisfying. So then it was quite interesting because we were very happy about the results, and the medical people, they talked about this in their cafeteria, and people got excited. And so the word spread. And so after 2 weeks, well, after when the paper was submitted, Frederick got the first call and said, there was a guy said, well, you know, we have a case like this. Can you actually try it, right? And the paper was not even, you know, reviewed, right? But you know, the method was there. So because that happened afterwards a couple of times, then we did this, of course, and we made this little nice sheet, which gave the information to the people, and so you can get the numbers and the diagnosis. It's in German, but Okay, right, so, and of course we clearly said this is an experimental method. This is not even reviewed. You know, we can do that for you, but just take it to the table of the tumor board and, you know, put it with very much care into perspective, right? So that's what we did. And then by the time the paper was accepted, there were already more than a dozen cases, but that was only inside Charité, right? And so then the paper appeared, and then there's this guy, Eric Topol. So if you are very, if you're familiar with any medical things, he's very vocal on AI and medicine. And so 4 minutes after our paper appeared online, he was tweeting about it and, you know, congratulating us, which was, you know, very nice. I mean, I don't follow this, but my medical colleagues did follow this, and we were very happy about it. Okay, so then I think I will skip this. Basically, we have further diagnostic applications, because sometimes you have to find the unknown origin of a cancer, and that works. And this is a nice one that just appeared in December, or, well, yes, it appeared online in December. And you see a lot of authors on this, and this is a very rare disease, sinonasal cancers. Luckily, it's rare. And we also used methylation data, and there the state of the art was that there were 2 groups of sinonasal cancers, and some of the patients in one group died, some of them survived, and other patients in the other group died or survived. And this was the state of the art. And then we did an analysis with the methylation data, and all of a sudden we found 4 groups, not 2, right? And then we analyzed these groups and saw that 2 of them assembled all the cancer cases, and 2 of them assembled the ones that didn't, you know, sorry, all of them were the cancer cases, but 2 groups were the non-survivor cases, and 2 of them were the surviving cases. So which was interesting, because you can do something about it now, because the medical condition is that people go and get the cancer out, then you do a methylation profile, costs $300. Then you see in which cluster you are, and if it's if this is the dying cluster, then the person can be treated very aggressively with adjuvant therapies and can be saved in many cases. And in the other cases, you don't have to do anything. So that was quite nice. Usually you just, you know, wait and see whether they survive. And then once this turns out to be to get nasty, then you try something, right? I'm really shortening this a bit, right? Please forgive me, right? Okay, so, and I still have a lot of things, because we are talking, asking questions, and so this is something completely different. Okay, we're leaving the field of cancer, and we are going into the field of history of science. It's a bit different, right? Okay, so here's the question. And I'm not starting with history of science, but we'll get there. And I just want your attention, right? And so here's what we know. It's old stuff. You know, we have models that measure the similarity between data, right? Between images, for example. And so basically you have these neural network models, and they give a number of the similarity, and they are trained, and that's it. So if you then want to understand why these models are considering something similar, you can also do LRP through them, but you have to do it a bit differently, because it's actually a higher order correlation that you're analyzing. in fact, this case, second order. And we developed a method which is called BILRP. And it's a Supami paper, you can look at it. And if these pictures are similar because these are two birds. And the reason why the model thinks it's similar is because of the eyes and the beak. Okay, so you see, this is a visualization of the, oh, sorry, I don't have my laser pointer. Okay, so this is a visualization of the explanation. And you can see that, between small cow and big cow and things like that. Okay, so there's this theory that we have, which is called deep tailor decomposition. Basically, it explains LRP in the way that, so in LRP, we have some kind of decision surface. And usually, if you want to explain a decision surface, then you could do a Taylor expansion. This, however, around one root point, this, however, takes arbitrary orders. And what we could show is that instead of doing a Taylor decomposition around one root point, we do a Taylor decomposition around many different root points, but we do a linear one. That is formally equivalent, but it takes some math to show it. So which then is the basis for LRP. But if we are, so that's the deep Taylor theory, and that basically says we can do it first order, everything. This is why this LRP thing is blazing fast. Now, if we want to go to a higher order LRP, then we just continue along the Taylor expansion and then, look at these terms. Now comes the history of science. Okay, so there's this wonderful institute that is also in Berlin. It's the Max Planck Institute for the History of Science. And I have several colleagues there, Jürgen Renn and Matteo Valeriani, who were he's the driving force behind the history part in his group. And so the question that they had was, they had books from shortly after the book printing was invented until 1650 or so. And the books were all textbooks on astronomy and math, right? So very math-savvy kind of books that were teaching the young generation in Europe how to compute the positions of stars and how to infer from a star position the time, right? Because at that time, history was often written in a way that says, and this star was in this position, and then this happened. But it was not, it didn't say, on the 25th of May, 2023, something happened, right? And so the books that we have, they are all, they're prints, but they're wood prints. And so they contain writing and numbers. And it's all over, they contain about 78,000 pages. And one of the questions they had was, if you want to understand how knowledge diffused across Europe, so you would like to know whose math is influencing, some other person's book and math, and how this was spread, how this evolved, and how this spatially and temporally spread. So that's the question. And for this, you would need to look at, so at that time, they didn't write down computer programs, but they wrote tables. The tables were like computer programs. From these tables, you could, these were actually ways to compute planet positions or something like that. This was the way an algorithm was implemented, like in the table. So if you then go from one place to another or one book to another, you would have to compare the tables. but the tables were sometimes copied to the next book fully, or they were copied in part, or they were copied, parts were copied and other parts were added. So if you are a historian that is a specialist on this, it's easy for you. You take some time to figure this out, but we tried to train a model that was taking 2 pages from a book and trying to find a similarity. And then we can measure this, and that similarity tells us the distance between books and times, and then we can look at the spatial temporal evolution of history. And so you can see that in this case, these are some numbers, and we say this is similar because of, so these 2 numbers are similar and these 2 other numbers are similar, and so on and so forth, right? So it's basically, there's an automatic process, but historians have a way to judge whether this makes sense. They can check it, right? But if you think about comparing 78,000 pages squared minus 1, then that's quite something. So okay. Anyway, so we studied this, and there's a PAMI paper, as I said, but there's also a manuscript that we will put online on this on the historical part, and you can actually get some very interesting historical insights from that. Because this time let me. Okay, so this time, for example, and that's not about the math, that they were thinking about climate zones. Okay, so what they did was they took the map and split it up into 7 climate zones. This was quite arbitrary. England didn't get a climate zone, right? Which was, of course, a disaster because the Royal Society didn't like it. But after a while, and this was like since the Greek, they had these climate zones. So then the question was, how would this transient to the modern climate zone that was 24 climate zones? Modern of that is 16 something, right? And so it turns out that the Germans in Wittenberg, where Gutenberg invented the printing, they actually added 2 climate zones, right? From 7 to 9. And of course, Wittenberg would get a climate zone, but there was also London who got a climate zone. And in this way, slowly the community, after a while of keeping this in parallel, started to be convinced that there would be a merit to have more climate zones. So this is interesting because you can track this spatially and temporally, and you can take into account all the historical documents of that time. And this is very much different than historians typically do this, who take one time point and one topic, and then they dig deep, and then they do this at another time point and space point, and they dig deep, and then they extrapolate. So now you have the continuous way of doing this. Okay, so I think, so I can either stop now or show you some reinforcement learning and robotics. Oh, I'm good, right?
I know.
Okay, so this is like I'm showing you different things that I enjoy having to. Yes, please. Yes, please.
So I'm curious whether you've looked. So you mentioned the LRP work, which
yes.
is about sort of understanding the
yes.
The responsibility of each feature.
Yes. Yes.
I'm curious whether you've looked at the temporal evolution of this feature, responsibility in relation to the convergence of your classifier.
Yes, we have, and it's interesting.
So I'm curious what it is.
Well, I mean, I think there's of course, I mean, you can look at these things, but there's, you can maybe, I think the problem, if you do that, is you have to look at many pictures. So you have to sort of do some statistics on this.
Yes.
So,
because the rate of convergence for these things will be different.
That's right, on the different pictures. So what you can do is you can create some anecdotal evidence, but the way we actually started studying this particular question was by converting a neural network into a kernel machine, and then looking at looking at the kernels, the outer product kernels that are in each layer, and do RDE, which is, you know, basically kernel PCA, and you look at the label. And then you can see that progressively overtraining, first from layer to layer, you suppress noise and you make the space, the relevant space smaller. That's number one. And the second thing is that, you know, as you train, you go from a more noisy thing to a more focused thing. So these are the two effects. And this is something that you would also see in NLP.
I see. Because the reason why I was asking was that I was thinking, is there a surrogate for the actual LRP in the training weights or some training stuff of the classifier that you can actually directly read out from the classifier?
Yeah, I mean, I think I understand what you're saying. The Clever Hans paper has this because we do a data-wide analysis on that. Yeah. So that's one thing. And you can also, you know, interpreting your question more freely, you can analyze, with LRP, you can analyze the weight of a trained network, exactly. And then you can use that for pruning. And if you use LRP as a way to prune, then it's, you know, you can throw away 90% of the ResNet weights and get the same performance. There's papers on all of these. Okay, so then, because I just added these slides because we had a discussion on at lunchtime. So this was in Science Advances, and it's a paper that I have together with an experimentalist and a number of my PhD students and you know, another PhD student. So I'm not expecting you to know what a scanning probe microscope is, but it has a 1 atom chip, and you can pick up atoms from a surface and write funny words with it, right? And this is a massive thing, right? This is like a room with a big thing inside, and that's the scanning probe microscope. And so the goal that they had was not to pick up single atoms, but rather to pick up molecules. Because if you can pick up molecules, you can build things. You can do nano robotics or nano building, right? Nano Lego, whatever, right? Okay, so here's the thing. So if you pick this up, you could do this with force feedback as a human, and you could measure all sorts of things. But you know, because you pick it up, and quantum mechanics makes this behave in a very, very nonlinear way, you lose it, and it falls down on the surface, sticks there again, right? And now you can, instead of having a human do this, you can have a reinforcement learning algorithm do that. And just by the way, this is highly non-stationary, because once this, you know, the tip loses the molecule, then the tip changes, because the atomic configuration of this single atom changes. So so we use reinforcement learning, and we put a lot of physics into this, and then we can see, hopefully, there you go. So this is the way these big institute, so RIKEN would do the same thing, you know, make nice videos. And
this is not simulation.
no, it's real. So you know, in a human, the best human that gets VR feedback and whatever has about can do this about 1 time in 50 times. Every experiment takes about 3 minutes, 5 minutes, depending. And this reinforcement learning thing does it in 48 times. So which means that we are able to actually play nano Lego and can create you know, things. And of course, if you think about catalysis, then catalysis is about structures on the surface. So we can systematically build them. Okay, so this is another, something is happening. Did you have the, okay. So here's something that I did with my Korean colleagues, which is our curling robot, which we called Curly for obvious reasons. And so I tell you what the problem is. I mean, I'm not sure whether everybody knows curling, but curling is this game played on an ice sheet where you have 20 kilogram odd big stones that you curl, that you give a twist, and that you have to throw 20 meters or so until, you know, the house. And sometimes people call, because it's a highly strategic game, so two teams play against each other. Sometimes people call this go on ice. And there's about 17 different types of throws that you can do with right curl and 17 with left curl. So it's quite combinatorial. And the action space is continuous. So that's quite a high combinatorics. So
with the wiping.
Without the wiping? We are doing this in the wheelchair rules, but we've also done it with wiping. I'll tell you about this in a second. So, but the first thing is there's extremely interesting differential equations on curling, right? So there's very elaborate ones. You know, they go over 2 pages. So people have really given us a lot of thought. In fact, in Japan, right? And so you can now build a simulator which simulates how the stone travels and how far it would go, right? If you would ask your robot to take exactly the speed, the curl, and the angle, then the stone goes really far away from the target point, about 2 meters away, which is not enough to win a game. So what we did was, so we had 2 components of this. One was a strategic component that could be solved with a reinforcement learning in the usual way, right? The deep reinforcement learning, and you just simulate this, because it doesn't matter whether you can take simulated data or not. This way you can understand what is which throw you need to take and what is the strategically best one, and it's like playing Go, right? And we use the same techniques as for playing Go. So shamelessly copying our friends at DeepMind. So then the question is, how about this real part, right? So because we know already, if we take the differential equation and the best strategy ever, this will be 2 meters away. And so we are compensating the error of the simulation, training a model to actually be able to compensate that. And there's another thing. So there's high uncertainty and there's non-stationarity. So the real interesting point is that the ice changes when you throw a couple of stones over it. And so, yeah, the interesting thing here is if you have that non-stationarity, if you have many people in the same ice hall, then the air gets more moisture, so it also changes. So you have to have an online adaptation of your correction term to the differential equation with very few data points. The curling rules say that you can throw, I think, 6 stones in the beginning as test throws, because you need to test the ice. Only 6, each team. And so they have a way to gauge, so to say, their throws. Okay, so then I've been talking to the, I mean, if you want to read about this, we try to put this into perspective and put this into a mathematical framework and machine learning frame. So that's in science robotics. So hopefully this works. Okay, so this is Curly, puts out his neck, looks at things, has an active computer vision. And then you see in the middle, you see the stone, right? So then it uses the computer vision to know where the other stones are, and also to see what are the kind of, what is the optimal throw, okay? Considering the uncertainty of the whole thing, right? So you go to the hog line, leave the stone, and then the stone travels. And yeah, there's a lot of little things.
Nobody's helping.
That's right. It's wheelchair rules. Okay. And
so the action space is the direction and the rotation.
Direction, rotation, and speed.
And the speed.
Yes.
Right. So is it that same fan out as a go? It should be less, right?
Well, it depends, right? Well, it depends. If you discretize things, then
okay.
But if
human as sweepers.
Yeah, but
that was we play wheelchair rules, okay? Yeah. So this was the best Korean high school team that we played against, and I think I'm somewhere on the side. So then again, it looks, and then so if you want to look at footage of this, it's really fun. We have, I don't know, a couple of 100 hours of footage, so you just get an impression of this. The interesting thing is that you can play. We played this in a number of games, right? We played this against most frequently against this best Korean high school team, because they were from a school close there. But we also played against the national wheelchair team, the national women's team, and the men's team, but that was not the national one, right? And so overall, over all these games, even against the not high school ones, we actually won, right? Not every game, right? So for example, one of the human teams, I forgot which one, they lost heavily, but they didn't take this very serious. And once they started taking this serious, it was too late. They would lose, right? And so we had a second game against them, and then they had the right attitude, and then they won, right? But only by one stone or so, right? So then we tried something interesting, which is having mixed teams. Because you could have humans are often nervous in competitions, so you could have the robot throw the stone, and there would be a human skip, right? And then there would be humans sweeping, and that was unbeatable, right? Because the skip really can read the ice, and the humans know how to implement what the skip says, and then that's fine. But you have to show the skip what throw will be done, what kind of, from these 2 times 17 throws, right? So that's a bit
like you choose where you want to put the.
Yeah, I mean the robot was doing all the strategics, all the throwing and everything, but you need to say this, tell the skip what the strategy was like, because in the usual game the skip tells the team what throw to make. makes this strategic decision, says, well, you have to throw it there.
So I'm curious whether it's a very interesting problem, because the strategy will have to now take into account the wiping of the guy, which it doesn't take.
That's a very good point. So I think the strategy has to take into account a lot of things. There's a lot of uncertainties. There's the swiping, but of course, if you play wheelchair room, this kind of uncertainty goes away. But the other uncertainty is the uncertainty which holds for humans and robots, that some of the throws are very difficult. So the standard throw would be like this one, where there's a small arc, or the takeout throw. That's easy, right? Comparatively, it's very successful, very likely to be successful. But there are some other throws that are very unlikely, and if you factor in the uncertainty, then the strategy will tell you not to do this throw. And there's also one other aspect which is interesting, and the precision in which you can control the X direction, right, of the house. That is quite high. It's like 50 centimeters or something like that. And humans are not better than that. But the
angle of impact.
But the Y direction, if you take the center of the house as the coordinate, so the Y direction is for I think bad players something like 2 or 3 meters, and for good players, something like 75 centimeters a meter or something like that. I forgot the exact numbers, but they are in the paper. So because it's really difficult to get the Y direction right, and because there's so much uncertainty with the eyes and everything. And so the sweeping is basically taking care of the Y direction. But if you do wheelchair rules, then you have no choice to readapt. Okay. Anyway, I think I've been I have already spent too much time. So I tried to convince you in many ways on the way that the black box needs to be opened. There's higher order XAI, and we have only talked about the bi-LRP. There's also, higher order XAI for graph neural networks, where we can go up to kth order. And that is actually, if you think about it, exponential. But there was an ICML and an ICLR paper that showed that you can convert this to something polynomial. So for the mathematical connoisseur, this is kind of nice. There's also things XAI available for unsupervised learning, clustering, anomaly detection, for transformers, and the understanding is really essential in the sciences. And what I alluded to was that quite often you can create very powerful predictive models, and the essence is that you use them to get some new insightful hypotheses that you have to test and scrutinize very carefully, independently. And in particular in the medical field, this has a certain protocol that you have to follow, otherwise people will not believe it. And so we are getting more and more into this medical field where we try to be predictive in our in our models, not predictive in the way that we usually know, but predictive in the sense that we, for example, if you have a drug test in a clinical trial, then the question is, can you predict whether a certain patient will be a responder or not? And these drug tests are controlled from an independent agency. So you cannot do post-hoc analysis. You have to do predictive analysis, and that is highly controlled. And that's a real challenge because, we're not used to that as machine learners. We always pretend that we're used to it, but it's not true, it's a lie. And all the things about uncertainty and calibration, I'm looking into your direction, that's really the essential and crucial part. And I think people in machine learning are not taking this serious enough. Okay, so I'm done. Thank you.
Thank you very much. Questions? All right.
I want to ask this question because I have many people from the group here. How do you keep students motivated to work on a 7-year project?
Oh.
How do you do that?
That's a good question, and I think I'm just stubborn. But I mean, I think that there were different generations of students, and so the first author became professor on the way. So I think, you know, I think honestly, I mean, I'm not joking, right? So I think that there's two ways to progress. So one is to do little steps, and that's it, right? And this is a risk-free approach. And there are some steps that take a long time. And it's also a lot of energy and a lot of faith. And it's usually, it's not, you know, students or the people that work on the project are not only working on that one, but they have also another risk-free approaches. But I think we need to, or I feel that I need to take the time, I have the responsibility to address very long-term difficult problems that take several years and to push the field forward. And you know, it happens that people get their PhDs in the meantime, become professors, get kids, you know, there's lots of things are happening. But in the end, everybody's happy because, you know, if this is done, if you get it, then, you know, like in this medical case, by the way, the methylation science translation paper, I think we did in 3 months or 4 months. So just to give a perspective, sometimes this goes very quickly, and the journal, I think, took 3 weeks or so. So that was really quick. So it's not always long term, but quite often the first step takes time. But most of the time it takes time because of the reviewers, even in the high impact journals, they are a bit conservative. So we have to ignore this. I don't, you know, I think people will go their path, you know, with the paper or without the paper. So that's not an issue. But to be on such a paper and to see that you know, stamina actually brings you to a different level, that is actually a very nice experience.
Thank you very much for a wonderful talk. I love the idea of using machine learning for science discovery. So I would have 2 questions. Do the medical doctors agree with your heat maps? So they are like, you know, same. Yeah. And the second question is, have you tried like transfer learning, like training the model of the one cancer and quickly like use that pre-training for the other one? Or does it make sense?
Yeah, we have done all sorts of games of that type. Yes. First question, yes, they like it, right? But only if the model is you know, has included all the prior knowledge and the bells and whistles that we should be doing. So it needs to be well validated, well calibrated, and so on and so forth. So we need to do our things well. And so transfer learning, I think that in the case, I mean, sometimes the representation is very useful for other decision making, but it's not a rule, right? So I think that, you know, one of the, you know, key insights that you have is, and that, you know, in transfer learning, often we have cases where there's so much data, right? And so in the medical domain, you often have rare diseases, you have long tail distribution. So we are currently looking at a case where there's of stomach cancer, where there's about 20 cancer types. 3 of them have 95% of all the cases. And so you may have only 3 or 4 data points in some of the classes. So transfer learning is a very difficult thing in such a context, because it's about stability, and the calibrations is part of it, and things like that. So if you look at the transfer learning models, they're not necessarily well calibrated. Okay?
Thank you.
but of course they, you know, I'm not saying anything against transfer models, but you really have to do this with very great care, right?
Thank you for the great talk. I'm really interested in your application for the medical things. So for the doctor, what they really need is not the number, but they need the lateral increment when you apply this method. So that's why when I heard that the doctor know your paper, immediately they ask you to try your method. But my question is like that, like the way in NIH and also National Cancer Center in Japan, we also have this very similar things. So I'm wondering in Germany, what kind of the document procedure do you need to net the doctor to use your method and to influence their decision? Because for us, like when we consult the lawyer and all the things, they find it's very challenging, very difficult like to rule out like in which part you can use it, in which part you couldn't use it. You have to get the approval from the committee and everything. So how do you do that?
I'm totally with you. This is a nightmare, right? Okay, so just keep it like that. So, but of course, you know, maybe to be, you know, stepping back one step. So I think talking to the lawyer first, maybe not a good idea, right? And so the medical community, if they would talk with the lawyer as a first point of entry, then perhaps they would never you know, have created the WHO rules, right? But for example, if you think about, but having said this, you know, it's a long path from some insight like that to changing the WHO rules, right? And on this process, of course, lawyers have to play their role, and it's very important to have them. So I'm not saying we shouldn't do anything with lawyers. We have to do this by the book, right? And the book in the medical domain is for good reasons a complicated one, right? So having said this, my dear colleague, David Kappa, who was one of the first scientists who was using this methylation, and he was doing this fantastic work. It's a Nature paper in 2018, where he was categorizing the brain tumors, and where he found many new brain tumors also with this methylation. And so we are now into 2023, and the WHO has changed the rules. So they have adopted the new cancer types. So I think this gives us hope that we can actually do something in this domain. And I don't know how he did this, but I'm quite positive. There are some very clear-cut cases. This is a very clear-cut decision-making process, where this is very useful. And I'm just also wanted to stress this once more. We are not doing AI to replace doctors. This is total nonsense, I think. We are doing AI to help doctors. Let's talk about the real problems in this world. Somebody, a friend who has been very much involved with pathology in China, he told me the following. I don't know whether this is true, but I can relate to that. So that if you don't retire any pathologists in China and have them work for 24/7, then in 5 years from now, you have a factor of 3 to 5 too little diagnosis. So which means that there's way too little doctors, and many people will die unless we have some way of supporting them. And of course, what is, you know, more important, even to train more of these pathologists. So there's two things that one needs to be doing. But support is very important. And just also one aspect, you know, there's this biological side of cancer research, and there's the clinical side of cancer research. And you saw me in this talk jumping from between both sides. And there's a big wide gap between them. And it's a very scientifically rewarding one, I think. And so also it's very, because there's this burning need to have support for pathology. This is also why after we discovered that our methods are actually useful in practice, so we founded a company. It's called AI Gnostics. It was founded in 2020, in March 2020. So we are a bit more than 3 years old, and then we have 80 people now. So people who have a very good machine learning background and who like to work on cancer and not on text or, you know, selling books, whatever, right? That may be a good possibility, because I think it's a very rewarding thing, not only because this is a company that is working well, but it's also rewarding in the sense that you know, you have you're helping an urgent problem, and you couldn't do this from RIKEN side, from the National Cancer Center side, or from the university side, you know, because you cannot scale this.
Thank you. Maybe one last one. Sorry, Klaus.
I'm there. I'm good. I'm waking up.
Yeah, I'm curious to understand what happens if there are. I mean, you talked about these kind of slices to decisions.
Yes.
I'm thinking what happens if some of those decisions, in scenarios when some of those decisions are either extended in the temporal direction or have additional dimensions for these LRPs. How would it work?
Yeah, that's an interesting one. I mean, so first of all, the temporal dimension in LSTM is exactly like that. Yeah. So there's methods for that, and you can get the temporal size. That's easy, right? But I mean, if the decision making has a temporal component, then, you know, usually you would have slices at different times.
Or yeah, that's correct. Yeah.
But there's also, I mean, if I take this question more you know, freely, then there's a, you know, big, I mean, this field of cancer biology tells you that tumors are often very inhomogeneous. So if you even look at the omics content on one side of the cancer and the other, this may be very different. And that actually tells you a lot about the prognosis. Yeah. And many other things in cancer biology. And just, you know, as a disclaimer, I try to learn about cancer, but I'm not a specialist. Frederick could answer this much better.
Yeah, because I mean the causality aspect becomes a bit weird when it has this additional
yeah. I mean, the point that I made was the spatial dimension, right? Yeah. Which also has the temporal dimension encoded, because the cancer has is growing, and that's why there's a temporal dimension.
Right? You could take the diff of two things and then sort of plus.
Yeah, but you know, I think that the point that I learned in all the interaction is that you can think about many things from the machine learning perspective that seem interesting, but there's burning questions that they have that you better solve first. Yeah. Okay.
Yeah, thank you for the wonderful talk. And I think your talk contains many things. In some part, you talk about history of science and evolution of knowledge. So my understanding is we try to find how this knowledge come from. For example, we finally found the kernel PCA come from you in 1996 or some years. Mm-hmm. So, but I'm wondering, like, what do you have any comment about? Can we use your concept for predict the future knowledge? Because I want to know which my paper will have high citation in future.
So, okay, I mean, that actually is easy, because you can ask your colleagues whether they like your paper. I mean, independent ones that you don't pay, right? So that's easy, this part. But I think, you know, so I think somebody said, you know, predicting is difficult, in particular the future, right? So I think So I think it's a very deep statement, right? But I mean, seriously, you could play these games, but you know, I think our governments and also people who you know, plan science, all of us, we're trying to predict what is the next big thing, right? We are trying to see what are the trends, and maybe we're also setting them, right? So the question is, and this can work, and a lot of people are just doing more of the same thing, right? That's one strategy, but there's usually also disruptive developments, and these disruptive developments are not foreseen usually. So I remember having a phone that was like this, right? So this was like you could put a nail into the wall, a good old Nokia phone, you know, that was really massive, right? And great, right? You could, you know, put it in the water and take it out and you still work. So and then, you know, came our smartphones, and this was something nobody foresaw. At least I didn't. Otherwise, I would have gotten more Apple stocks. Right. So I think it's the same in the science field. So you know, I think the good strategy in the science field would be to do the things that matter to you and that you're enjoying and that you find interesting, and that I think is the best bet that you can have. Because I think the only thing that you can do good is the thing that you enjoy doing and that you find motivating, right?
Okay, so let's thank Klaus for the great talk.